Hey guys, this is Gym Term 2A, first practice midterm for midterm 2. This is going to be the video walkthrough with the review at the beginning of this. I apologize for taking a bit of time or really just slacking off on making this. I've just been really busy this past week, especially this weekend. So apologize. I'll definitely make sure to get this and the second one done pretty much tonight. It's just I've been busy. So what I'll do is I'll release keys for all three, and then if I do a video midterm for the third, I don't know if I'll do one for the third one, but definitely for the first and the second one I will. But I'll update the key, I guess, and I'll throw in an updated key, so that way you guys have something to look at. And I'll probably handwrite the key this time because honestly, chem drawing these keys takes a while, especially these, well, actually, I guess I could still actually no. I guess I don't need to. I probably will just be. I'll be a little lazy on this stuff because at least for midterm 2, the midterm 2 syntheses are a little long and they're a bit tricky. These are a bit straightforward, so I could probably at least get the chem draw on them. But anyways, cool. Midterm 1 just happened, and I know that it was a very mixed review, very mixed response. Half people liked it, half people didn't, and whatever the case may be for you individually, hopefully this exam kind of jumpstarts you and reminds you what it feels like to take an OChem exam. And I mean, it's spring quarter, right? Everyone wants to be done with the year, and everyone can see. I mean, we can see the end is near, right? It's so close. We're almost done. So we're almost at the end there, and we're really hoping to hit that finish line, right? To finally finish this marathon we started back almost a year ago. So just keep your heads up, right? Keep your spirits up. We're almost done. If midterm 1 didn't go well, it's okay. There's a drop, and we'll just do well at midterm 2. Okay, cool. So again, plan this video. We'll do a little bit of review before we hit the reactions, and then we'll go through the mechanisms, hit the synthesis, and then talk about any other variations we can. Right. Again, biggest thing is what can I do when I don't have a lot of problems, right? How can I help myself succeed? Okay, cool. So with that being said, let's just get into it. Let's start the review. Because there is, I mean, you guys have seen the study guide, there is a lot of reactions. Because of that, I will pretty much, we'll go through mainly reactions and anything in particular that I think is important for any concept stuff. So actually, let me just pull up the second midterm too. So for any concept in midterm 1 or practice midterm 1 or practice midterm 2, so let me actually even go share those pages right now. So for example, like concepts like, how do I solve for this, like acidity or, of amine or a phenol or, stuff like that. We'll go directly through the question, like in that question, we'll talk about that concept. So basicity and reactivity, right? We'll talk about that. But because of the sheer amount of reactions, I won't even lie to you guys, actually, right now, in front of me, I have your study guide, just because even I can't keep track of all the things you need to know. I mean, it's a lot. I think I mentioned it before too. It is a lot of reactions. Okay, cool. So with that being said, let's just get into it. Let's talk reactions and what we need to know. So chapter 21 is the chapter of the amines. And so the biggest thing about amines, right? I mean, we've seen them all quarter, right? This is not anything new. Amines are exceptional nucleophiles, right? They are low in electronegativity, right? They're to the left on the periodic table. That lone pair is super available, and it's really willing to go out and attack things. So back in the day in A and B, we kind of just said, do your reactions as we tell them to. It's totally fine. So for example, one reaction, one reaction is the addition of nitrogens into carbonyls, right? And so what we would get, depending on the nitrogen, is like imines or enamines, stuff like that. So if it's like primary, right, it's an imine. Secondary would give you the enamine, so like something like this, right? So no one should be surprised, hopefully, at the nucleophilic capability of an amine, right? The other thing that we kind of whisper at the end of that every single time we talk about amines is that amines are also very good bases for this reason, right? Again, they are not very acidic, that lone pair, right? Because it's very much to the left of the periodic table. So the ZF of that nuclei is very low. So protons are very much attracted by those electrons, right, on that amine. So amines are great bases. I mean, we've used amines all quarter, right? TEA, that's what that looks like, triethylamine, or pyridine, right? These are what we think about when we think about amines. Okay. And so, actually, I guess I said I wouldn't talk about this, but I'll talk about this very briefly, just some quick concepts to know. So you can be asked to determine, what dictates the basicity of an amine, right? What qualities to look out for, what to know. And so here's a couple of guidelines. You can really just split these up into groups here. Right, SP, SP3, SP2, and SP. It's not what I wanted to do. There we go. Oh, no. Okay, whatever. I'll just rewrite it. Give myself more space. Yeah. Okay. The SP. Okay. And if we think about hybridization effects on atoms and what it does to acidity and basicity, you might remember that basic things are more sp3-like and acidic things are more sp-like. Again, it's all orbital shape. So these are our bases and these are our acids. Okay. So if I think about, I mean, probably the easiest one to resolve right now is the nitrile, right? The nitrile is the most acidic amine, right? Absolutely the most acidic amine. That is a non-basic lone pair. Okay, let's even give it a color. Okay, so don't expect nitriles to do a lot of the reactions you would want to do. For example, not really going to do SN2s. They could be motivated to do SN1s, right? Cations will motivate almost anything to attack them. So that might be something worth thinking about. But aside from that, not very willing to pick up a proton or really attack electrophiles. Usually the value we'd use for this is about like -5. Like it's very, very low. This nitrile does not want to pick up a proton. When we think about hydrolysis conditions for a nitrile, super, super rigorous, right? I mean, we're thinking worse than an amide. Because these guys are dehydrated amide, so very, very rigorous. So absolutely the bottom of the barrel of a base. You would never want to use that as a base or consider it a base. But when we move up to the sp2s, we're allowing more basic character to leak through, and we have much more reliable bases. So for example, I mean the epitome of an SN or sp2 center or sp2 nitrogen, sorry, is the imine, and so the imine lone pair is much more basic. Usually these guys clock in around 5 to 7, depending on particular qualities. Okay. But yeah, these guys can pick up protons. I mean, we've seen an imine in action before, right? We've seen pyridine, right? Pyridine is a great base. It's also a very good solvent too, organic solvent. So you can solvate things in this and get a free base also with that. Okay. So this lone pair, pretty basic. Right, you'll go out and pick up a proton. In the 5 to 7 range, I'll give it a number of, I'll give it 6. Okay, we'll give it 6 for that lone pair. Okay. So again, nitrogens that are double bonded, clearly sp2, going to act like imines, right? And this is actually going to be very important for heterocycles to understand that nitrogen is basic, because we'll see that will dictate a bunch of chemistry when it comes to pyridines when we talk about that. Okay, cool. Now, another type of sp2 base that may not be super obvious is the aniline, right? Aniline looks sp3 because, I mean, it's a nitrogen with 3 groups or 4 groups on it. But keep in mind that this lone pair here, it is next to the benzene ring, so it can resonate. And in order to resonate, it has to be sp2, okay? But this base here, right, because this lone pair is resonating, right, it's going to be slightly more acidic than other sp2 nitrogens, right? For example, this is non-resonating, so it's just always localized to N. It's like the standard, the golden standard, right, for the amount of basicity that an sp2N could have, right? But this lone pair, while being sp2, also resonates, so we increase the acidity of that lone pair, right? So slightly decreasing the basicity. We clock this in at about 4 to 5, right, as we expect that amine to be. Now, on the flip side of that, right, is there any is there any secondary amine bases that, increase in basicity, right? That would be this example here. This is called the imidazole. And so on the imidazole, we have 2 lone pairs, but the lone pair we care about is this one here, right? The sp2 looking amine, the pyridine looking amine, okay? And on the imidazole, this lone pair is particularly basic. If I had to give it a value, I would put it right at 7. And so why is that? Why would I give that a value of 7? It's because the imidazole has the lone pair on this nitrogen next door that can assist by increasing the electron density on this nitrogen. So not only do we have, the localized lone pair on nitrogen, but this nitrogen over here is sending density in, right? Now, be very careful. This is not a lone pair resonance stabilization. Like a lot of people associate resonance with always being a stabilizing force, so it always increases acidity. right? That would be the case for this lone pair here. So if this orange lone pair resonated, then yes, that would be more acidic. But the point here is that a neighboring lone pair can enter the battlefield, right? It can join this nitrogen in attacking other protons. So we're increasing the electron density on this nitrogen. Okay. So way to think about it, probably the best way is this nitrogen, right, or this imidazole N can increase its electron density on this nitrogen, right, by receiving electrons. But this aniline type N, right, gives up its electrons, so it's lowering its electron density. So that might be the best way to think about it, I think now, right? We're lowering electron density in this example. That says density. I don't want to write it out. But here we're increasing electron density on that nitrogen, right? And so that's why we see increased basicity. Okay. Now you don't need to go out and memorize all these examples, right? You don't need to memorize that aniline does this, imidazole does that, and pyridine does this. What's important is to understand the effects that we're looking at that dictates why one base is better than the other, right? Cool. Now, one last example that I'll keep you, or I'll show you guys is the pyrimidine. Right, so hopefully you guys understand what pyrimidines are. That's a bio thing there. But anyway, this is a pyrimidine. And so pyrimidines very, very paradoxically have two lone pairs, but are incredibly non-basic. Well, not non-basic, but they're really low. They're around the aniline in terms of basicity. So what's up with that? Why is that? Why is this lower? Why is this more acidic? And it's because despite the fact that there are two lone pairs, we have two inductive nitrogens that are pulling on electrons. So they're essentially pulling on each other, right? And they're actually increasing the acidity via induction of that lone pair. Okay, so cool little effects, things to think about. But yeah, so that's all I'll say for that, just to save on time. But those are sp2 bases and what to think about. Last thing is going to be sp3 bases, and as you can imagine, we do have a pattern for sp3 bases. Generally speaking, in the gas phase where there are no intermolecular interactions mostly, or no solvent interactions, right? Tertiary amines are better than secondary amines, or they're more basic. So actually, let me put it in this order to follow the arrow. So primary amines are less basic than, or sorry, ammonias are less basic than primary amines, followed up by secondary, followed up by tertiary. Right. And so this is just a function of how many alkyl chains there are, or how many donating effects do you get. Right. So all this there. Right. But when we consider the liquid phase, something really weird happens. So ammonia is still the worst, but now tertiary amines are the next worst base or the most acidic, followed up by primary and then finally secondary. So in solution, actually, the best bases are secondary amines. And the reason for this is because in solution, we have hydrogen bonding interaction. So if we have a proton on these guys, which I'll add in, right, that cationic charge, right, is stabilized by intermolecular H bonds. And in order for you to maximize them, right, you need to just have maximal surface area, I guess, or ability to, just area to H bond. And in the tertiary, there's too much steric hindrance. So lack of solvation, right? Solvation shell is what forces that tertiary amine so low. Okay, cool. So these are the major trends to understand for SP, SP2, SP3 amines. And for the most part, sorry, this over here would be like 8 to 11 or 8 to like 12 usually, or 8 to 11. But yeah, these are the trends to understand. When we talk about the basicity question, we'll come back to this anyway, so we'll have another time to talk about this. The only last thing I'll leave you guys with is that there is one amine that is incredibly non-basic, almost as non-basic as the nitrile amine, despite not being a nitrile, and that's the pyrrole amine. And I don't really think I have to explain too deeply why this is the worst. If we consider that this is a ring, right? It's cyclic, conjugated system. It's planar, right? Hopefully you guys see where I'm getting at. This lone pair is aromatic. And so if I were to protonate on that amine lone pair, right, we would be destroying aromaticity, which is a big no-no. So absolutely non-basic. In fact, if you were to protonate on this amine, it would occur at the carbon and not at nitrogen. So that just shows you that lone pair is definitely delocalized. It's not actually on that nitrogen. Cool. All right. So that's all we'll say for basicity. Okay. But let's now get into just reactions of amines. And again, we'll kind of speed through this a little bit. If there's any important concept, I'll take a second to stop and talk about it. Just that we got to, we also got to power through chapter 22, right? And I want this video to be less than 3 hours. So cool. All right. So preparation of amines, right? I mean, we've talked about this already. There's a couple of ways we can make amines. Probably the most memorable way as of right now is you can add in a nitrile and then reduce that nitrile like with H2PD or, LAH, that's just lithium aluminum hydride, right? Either one. And that will give you the primary amine. Okay, so that's the way we've already talked about. Pretty simple, right? Nothing too crazy there. We can also take another route here. We can use NaNH3, which just replaces this with an N3. And so, I mean, you guys hopefully now you guys understand how this works. Because you guys went over the mechanism for this in class. But you can reduce off the N2, right? It's a very powerful leaving group. And a very, shitty but quick way of thinking about this. It's sort of like an SN2 type thing where you kind of get rid of the N2 group. You can also think of it as it's if you're kind of like, oh, that's kind of weird, I've never seen that. You can also think of it as a double bond. This might be the easiest way to think about it, actually, where an H minus sort of reduces this and then reduces it again by doing kind of like 2 subsequent SN2s, or yeah, kind of like that, but whatever. Anyways, you guys get the point. You can reduce this down into the NH2. Okay, cool. Now looking at these two methods, right? Can I see something that tells me when to use one over the other? You totally can, right? This has 2 carbons. This has 2 carbons, right? So you can kind of see that in the nitrile example, we add a carbon. We have 3 carbons now. So if you need to add a carbon, make a primary amine, this might be your way to go, right? It's totally a viable pathway. The azid, right, would say the same. Cool thing about azids, azids are actually very explosive. So about 8 in 10 reactions work perfectly fine. The last 2 will always kind of explode on you. Every time you kind of use azids, you always use something what we call a blast shield. So you'll have this sort of spinning or whatever, and you'll be behind sort of this like glass, or not glass, but you'll be behind a shield that will blast you from any explosion that's possible. So pretty cool, right? It's an explosive, and you can imagine why, right? N2 can be released, and N2 is incredibly exothermic. That's why a lot of explosives are surrounded around nitrogens, because the ease of N2, or the how easy it is to make N2 from a molecule determines usually how explosive it is. So I don't mean to ramble, but I'll talk really quickly. But there's you can find compounds online of these completely nitrated or completely azode or completely nitrogened molecules that are proposed that people want to make but can't, because if they try to, I mean, this is literally a bomb right here, right? I'm put on a list just for drawing this out, right? But yeah. Cool. There's what it's called azid, something like that. You guys can look it up. I'm pretty sure it's called azid. And that's like a proposed explosive that's all nitrogen. So cool. All right. In terms of, again, old pathways we can talk about, I guess the most traditional is you take an NH2, right? You kind of throw some hydrogen at it or some kind of reduction sequence, doesn't matter. And you get the primary amine. Okay. So again, these are kind of old-fashioned ways, like SN2 styles, or starting from the arene, right? Reminding of these because these sequences are important to remember, especially for chapter 22. Okay. But kind of the new ways, some of the better ways to do things. There's one more way. There's the Hoffman. Almost forgot. So primary amide, Br2 OH minus H2O, right? That gives you again, I like to think of it as you're replacing the whole amide function with an NH2. You can think of it however you want to. You can think of it as erasing a carbon, whatever you need to. I prefer thinking about it this way. Okay. Cool. But the first method that we'll talk about that's really a better way, and it's much more important synthetically and industrially, is the Gabriel synthesis, which for the most part is one of the most choreographed reactions on the planet. I mean, you'll know when you see it because there's nothing else that it could be. But actually, I'll even start from here. The phthalic diacid, But phthalic diacids, you guys learn, you heat up these diacids, especially in the presence of an amine. And what you get is the phthalic or phthalimide. So you form the phthalimide. And the phthalimide proton is particularly, it's pretty weakly basic. It's around like 9 or 10. So it's not bad. It's about the same as a thiol. So chemistry that a thiol can do, this guy can probably do too. But you can deprotonate it pretty easily with like bicarbonate, and make the anion. Okay. And then this anion here can do pretty good substitution reactions. Now, remember, usually the general rule of thumb is methyl or primary, right? Try to stay away from secondary tertiaries, but I'll go ahead and say that because of the pKa, because it's not that basic, secondary might be okay. Okay, but I mean, for the most part, you kind of want to, stick it to methyl and primary substrates, because those are the ones that just do SN2 best anyways. Okay, but anyways, let's say we just did Rx. We can add that on, and then we can do a hydrolysis sequence, right? So sorry, yeah, that'll work. H3O plus in heat, and that will kind of liberate out the nitrogen via 2 amide hydrolyses, right? And imide is just 2 amides anyways. Oops, sorry, that should be OH. OH. Technically, you'll form the amine salt, so the ammonium. But I'm pretty sure in this class you can assume that there's some OH minus afterwards, but I'll write it in, right? That we'll do OH minus after, okay? Which will make this not the salt, so it'll dissolve into solution and you'll have it very pretty. And then technically these will be O minuses, okay, because we'll be in base. Cool. So this is a very great way of making primary amines if you need to. As you can see, as we predict the products, the sequence is pretty choreographed, right? I call this the Gabriel reagent, right? Because you see it, you know exactly what it is. You can't really confuse it for anything else. And we'll see it again at the end of the quarter too for doing something else. All that really changes is what is Rx, right? And then it just tells you what the primary amine is going to be. So every Gabriel reaction is essentially, it's going to have an NH2 in it, and then whatever the R chain is, you'll know exactly what it is based on the question. Okay. You can also use this to make primary amines in synthesis too. So, like, let's say you started from a bromine, you could theoretically on an arrow, I know it feels weird, but it is fine. You could do this. K2CO3, and then put the whatever the, or I guess, yeah, that would work. And then you would have to draw the adduct and then the hydrolysis, right? Or I guess you could possibly shove it on an arrow and then just show this as an NH2. So the Gabriel reagent is just, if you think about it, it's like a large Amazon truck for an amine. It's just delivering an amine. That's about it. Okay, cool. So that is another way to make primary amines. And again, very important synthetically, especially in peptide chemistry. Peptide chemists use this a lot. Okay. But by far the number one reaction for doing or making any kind of N bond, primary, secondary, tertiary, is the reductive amination, or what I call the red am. Okay, so how does the red am work? Well, you guys already kind of know how the red am works. The red am begins with, right, an amine that you can, actually, we can start from ammonia, right? Ammonia, which we can condense with any kind of carbonyl. I'll just choose this aldehyde here, okay? And so the general trick is that for primary, secondary, for all of these amines, actually, you can always just replace the oxygen with the N, right? And just get rid of a proton. So you get here the iminium, okay? Iminium ion. And then this iminium we can then reduce with a selective reducing agent, or a weak one. NABH3N is usually the one that we use. You can use, I know you're told like pH3, pH4, you can write that in the air if you want to, okay? And that leads to the reduction of the bond, leading to this product here, okay? So this is the reductive amination. You're essentially doing 118B chemistry and adding a 118A step. You are just you're forming the NC bond and then just reducing that pi bond you don't need, okay? Now, why NABH3CN, right? Why not NABH4? It's because this reaction, red am, is what we call a one pot. So the meaning of one pot is that we do all this in one round bottom flask. And if we did all this together, right? So if I have this here, right, you want to make sure that whatever reducing agent you use does not also reduce the carbonyl. Otherwise, you're going to have a bunch of amines and alcohols that are just kind of hanging out together. So if I used NABH4, that will reduce the carbonyl. So kind of a problem. So we use NABH3CN and also at a slightly acidic pH, because One, the iminium is more reactive than the carbonyl. Yeah, that's about it. Yeah, I don't know why I said one. It's really just that the iminium is more reactive, right? And so that we'll get. The mechanism is on your slide, so if you need to see it, you can look at it. But again, this is an old mechanism, so I'm not sure how much weight that carries, but it might carry some weight. But all I'll add here is that it just does the same kind of reduction sequence that you would expect, right? Cool. And you can make any type of amine with this. So I could even take this primary amine. And then let's say that I decide, you know what? I want to add this ketone. Okay. That's totally fine. The overall cue, really the signaling element is the NABH3CN and a carbonyl, right? NABH3CN kind of tells you that you want to sort of, form that NC bond. And again, it is the most reliable way to do this. So all I'm doing is I'm essentially replacing, it's like I'm erasing the ketone here, or the carbonyl, and I'm just bonding the nitrogen to here, right? That's all I'm really doing. Okay, cool. So reductive amination, probably one of the best, absolute best reactions you can do. Now, one thing you'll notice about all these syntheses back here is that, I guess with the exception of the of this Gabriel, because technically you could kind of make you could argue that you can make a secondary, but for the most part, you'll notice that these are linear primary amines, right? At the very least, for these here, all of these groups, I guess also an exception is this, depending on what R is. But anyways, all of these groups usually have some kind of CH2 sticking out. The red am offers you a very reliable way to make branch centers, right? Alongside also reliably making linear centers as well. Okay, and by linear, I just mean like a CH2, right? There's no branchingness, right? So red M is very, very good at this. Aside from that, that's about it. Nothing too crazy. Just keep in mind that with this opens up the possibility of intermoleculars. So just keep that in mind. Again, we'll see with another type of reaction that we could possibly have a bunch of components adding together. Again, what really gives away this reaction is usually the NABH3C, and that tells you what you want to do. So pH about 4. That can attack there, 1, 2, 3, 4, 5. So we'll make a 5-membered ring with this nitrogen. And again, it's just going to reduce down anyway. So I'm not too concerned, but I'll draw on the H to kind of show where that is. And then again, I mean, we have 1, 2, 3, 4. 1, 2, 3, 4. So I'll have to make this, wait, 1, 2, 3, 4, 5, 6. Wait, 2, 3, 4, 5. Oh, I drew this a little bit too long. Sorry, my counting is not good today. But anyways, then we could just do this here. 1, 2, 3, 4, 5. So we've made this sort of, this is actually, I forget which, this is a body for a drug. I forgot what it's called, but it makes something called retronescin. I remember that. Okay. So just keep that in mind. That's a possibility. Okay, cool. All right. Now, why is it that we're bothering to do all of this work, right? Why is it that we're learning different ways to make these NC bonds? Oh, I just remembered there's one that I forgot. I guess you could also do this too. You can acylate and then reduce. That works too. Not bad. So LAH here. Okay. But again, well, actually, so first off, one question I get is, so this reaction here, the LAH reaction, this essentially does the same thing almost as the as a red am. Well, I mean, it's pretty much the same in terms of making NC bonds. The only thing is that with the red am, with the LAH, this has to be linear because of the carbonyl. People often ask me, what's the difference between this LAH reaction and the red am? And the answer is not much other than the branch aspect. You can really do either one as long as it accomplishes what you want to do. Just keep in mind that LAH is super reducing. So practically speaking, if there's other reducible components on your molecule that LAH could touch, you might not want to use it. But other than that, I wouldn't really stress about making the choice over one over the other. But like, for example, let's say that I had like an ester on one side, I had an amine on one side, and I had to, alkylate the amine. I'm a little wary of going the LAH route because the LAH route will also reduce the ester, right? Esters are more reducible than amides anyways. So, it's a way to think about it. Okay, cool. All right. But anyways, like I was saying, what's the whole point of us worrying about this, right? Because again, back in the day, what we would do is we would take amines and we would just do SN2 on them, right? Like we would just do like something like this, CH3I. And that is true, but it turns out this reaction actually isn't as clean as we lied to you guys as it being. Turns out that amines actually are notorious over-alkylators because eventually this proton is lost, the lone pair is rejuvenated, and we just get over and over and over alkylation. So in this case here, right, absolutely impossible to stop. Almost always, 99% of the time, you will proceed to what we call the quaternary ammonium salt. So whatever the halide is, in this case it's I, right, counter the salt here, will make the quaternary ammonium. Okay, the quaternary ammonium salt, which at least for SN2 purposes is kind of not salvageable. It's kind of, the reaction is now dead in terms of the SN2. But this is, we can still do something with this. We can take this amine and we can expose it to pretty basic conditions. So the basic conditions being Ag2O and water and heat. So this is an elimination sequence. And we can essentially forced elimination, okay? Because the NR3 leaving group is actually not that bad of a leaving group. You guys might remember NR3 is super deactivating, so it is already willing to take electrons. So as a leaving group, it's not too bad. So this is known as the Hoffman elimination, and it can be a very sneaky and strategic way to make double bonds from amines. So alkenes from amines. What's really important to understand about this reaction is two parts. So first part, so I have this amine here, right? We have an excess or an exhaustive methylation. Okay, we have an exhaustive methylation. So this turns into this here, okay? And so now we can do our Hoffman elimination. So like the name would suggest, this is the Hoffman elimination. Hoffman, right? Hoffman meaning the less sub position. So whenever you do Hoffman eliminations, I would always recommend marking your alpha carbon, which is the carbon bound to nitrogen. And then every carbon bound to that dot is a beta carbon. So these three here. Technically, these guys are alphas, but they don't have beta, so we don't care about them. Okay. The trick to Hoffman is the least sub beta, so the least sub blue spot is going to be where the elimination occurs. So as long as you follow that rule, you'll never have to worry about anything, right? In this case, this beta will always win. Okay. And we'll form this alkene here, and we'll form our trimethylamine. Okay. Cool. So, so if let's draw the exact, so it'll form this, but really what this is this here. So same thing is just kind of, drawn weird. Okay. So Hoffman elimination, right? First thing is that, hey, if I do a Hoffman elimination, right, it will always form the alkene it'll form the alkene that's born from the least sub beta carbon. Okay, so this is really important because there are always some examples where you can draw these amines where you can have sort of competing betas. So for example, what can I draw? Yeah, so something like this, right? If I have this here and I do the CH3I excess, right? Again, we'll form the ammonium here. And then we'll do our elimination. And so when I do my elimination, again, I'm just marking every carbon that's alpha, and then every carbon marked, connected to those orange dots are going to be our beta carbons. Okay, so we have, oh, sorry, not this here, right? We have beta, beta, and beta. Okay, again, the least sub of these, if all I focus on is which of those blue dots is least sub, I automatically get the right answer, right? It has to be this one. Okay, and so I'll form this here with this nitrogen product here. Now, why is it really important to focus on the less sub component? It's because if you were to just think about least sub alkene, right? That's what often is taught in this class, is just look for the least sub alkene. You'll realize that elimination on this side will also give you a primary. So we have two dueling alkenes, or at least two dueling beta positions, which are actually not really dueling, because if you apply again the least sub beta carbon, you never have to worry about this. You're not ever stressed about which one wins. Always think about less sub and you'll be fine. Okay. Cool. Now, with that being said, right, all talk else about the Hoffman elimination is that you can also Hoffman eliminate on rings, as always. And again, one common mistake I see people do all the time is they'll do something like this. And let's say they want to completely eliminate off this. So they want to eliminate here and they want to eliminate here. they'll do this in one step, which is impossible. Every cycle of Hoffman gives you one alkene. So you can eliminate once. So we can eliminate one. So we can cut off on that side there. Give, add the methyls here, and then say this is double bond. And then if I want to eliminate again, I can go ahead and do that. But I'd have to eliminate a second time. So just keep that in mind that you have to eliminate. Keep in mind that you have to, when you eliminate, you only eliminate once per cycle. So don't just, if you need two alkenes, don't just do it in one step. You need to do it one at a time. And we'll see an example today of where we needed to know that specifically. Okay, cool. But again, with time and all that, let's just, keep moving forward. That's the Hoffman very quickly. Most important concept in anyways. So again, that's a way to sort of salvage the Hoffman reaction. If we could salvage it. Okay, cool. So all that's left now are the Manic and the nitrosation reactions. Manic is pretty simple to talk about. Manic is if you decided in the middle of your reductive amination, your red am, that you actually wanted to couple an enol instead. So how does the Manic work? Manic is very simple. You start with some kind of amine, and I'm using a primary here, but it could really be any as long as it can form an imine. I guess tertiary means the only one that's kind of not allowed to be used here. Some kind of aldehyde and some kind of ketone usually. So the most traditional examples are usually something like this. Okay. So how does this reaction work? So the amine couples with it reacts with the more reactive of the carbonyls. So we'll use a mildly acidic conditions. So first step is amine plus aldehyde usually. And so again, for these reactions, we want the aminium. So you're just essentially replacing the aldehyde O with the N group, and you lose a proton. Okay. While on the side, you're also tautomerizing the keto into an enol. Okay, so we'll just go ahead and do this. So then we're doing a keto enol tautomerization. Okay, and you can do that in acid, right? Again, if you need any arrows specifically, I would look in your slides. The very quick way of thinking about this is you're taking this proton while this pi bond is taking a proton. That's how it's catalytic. But anyways, these are two setups. You make the imine and you make the enol. The third is just their reaction together, their marriage to form their bond. But the enol essentially just attacks the amine to give us in total this molecule here. Okay. Now again, I'm being very quick with my arrows here just for the sake of time, but essentially we're making this here, which is a beta amino carbonyl. Okay. So that's the Manic reaction. Okay. It's instead of introducing a reducing agent, you introduce a nucleophile, which is the enol in this case, and it adds on the imine on that alpha position, right? So really, you're forming this alpha beta bond here, right? Now, some of you might recognize this reaction is very reminiscent of the aldol condensation, that is true. The Manic is actually the amino analog or the aza analog of the aldol. Okay, so what the aldol can do, the Manic can do as well. So one little thing I'll tell you right now. The aldol reaction primarily, right, is used to form these enone compounds. Okay, Manic is actually considered a milder version of this, and I won't go into the reasons why, but essentially you can do the same thing. You can heat it, or you can do, think about it. If I wanted to make an alkene from an amine, right, I just do a Hoffman elimination. Right, and so what you'll get usually is this here. Okay, is the enone product. Sorry, like that. Okay. Now, really what this is used for is not for desubstituted. So really when we do this reaction, because you can imagine, right, if I have this here, we have this competing beta proton. Really, this elimination reaction is used for when you want to have this CH2 here. So I'll keep it, I'll keep this over here like this, right, to symbolize that, oh, we usually use this reaction for the CH2 enone, but the reaction or the product of this reaction is this. So actually, you know what? Let's do this not to be confusing. I'll just draw the manic that you'll usually see this done for, which is this here. Okay, cool. CH3 excess, then OH minus in heat. Okay, so this is usually the manic that we tend to use to form this enone here, right? Again, this is a solution to a usual problem that we won't get into. Okay, cool. All right. Outside of that, with the manic, what you have to understand is how to work backwards on these problems. So for many months, many days, I've always preached the word of retro, and for many of you, it fell on deaf ears. Well, now you need to know. Now you need to know a little bit of retro and how it works. Okay, but the retro for an manic is the same as the one for aldol. So an aldol, right? The retro is you cut between the alpha and the beta, and now you get as two carbonyls usually, right? Where the alpha is unchanged and the beta, you kind of mess around with a little more, right? We turn to a carbonyl. Manic is exactly the same. You cut between the alpha and the beta, you get an alpha fragment that stays the same. The beta fragment turns into an imine, which you can further cut into a carbonyl and the amine itself. Okay. Oh, sorry, I lost an R group here, which I already know I'm going to get questions about. So I am predicting that. Cool. So you'll get these two components here. Okay. So pretty simple. Not too bad. So we'll get this, and then we'll get the primary amine in this case. So that's the retro. That's all you need to know. Okay, cool. So you could potentially be asked a question of, what does this amine come from? Or sorry, where does beta amino group come from? Okay. Now that beta amino component is really important because this could be a synthesis question too, and you'll have to know what it looks like. And it could also be present in other ways like rings. Rings are probably the hardest way to see these kind of reactions. I actually there is one on the practice midterm that's a bit hard, but I'll try to write one here that's a little bit easier. Again, how can you figure out that this here is a manic? This almost looks like the reductive amination thing we did. Super simple. You'll just see mild acid. You won't see you won't see the reduction part of a reductive amination, right? You'll just see the mild acid. So in this case, right, again, this will couple 1, 2, 3, 4, 5, 6. So we'll get a 6-membered ring here. And then we'll have this here. Okay. Now keep in mind, right, it's the aminium that we're reacting with here, and we're reacting at this carbon. So I would count 1, 2, 3, 4, 5, 6, 7, 8. Right, this is 6 and this is 8 based on the alpha carbons. So the one we want to analyze is going to be this internal one here. Okay, and so this is going to go ahead and attack here, which is also going to make a 6-membered ring. So it makes a very similar body to the reductive amination, but the difference here being, sorry, let me draw this a little bit better. There we go. The difference here being that the carbonyl is on the outside of the ring. Okay, and if there is a carbonyl, again, looking out for this beta relationship will kind of always signal to you that this is a manic type reaction. So imagine you had to reverse this. Super simple, right? You just kind of cut here. That tells you, again, between the alpha and the alpha fragment stays the same, but the beta fragment, you'll turn into an imine, and then we can cut here once again, which will tell us, right, oh, okay. Right, we had something like this, which is this monstrosity here. Okay, cool. All right, that's the manic reaction. There's a couple questions on that, so we'll see them. But again, manic versus reductive amination, it's a matter of NABH3CN versus just mild acid. But yeah, most of these are just 3 components. Throw 3 things into a pot, stir it over some heat, put a little bit of acid in it, tends to work out. So yeah, cool. And with that, all we have left now is the nitrosation reaction. So we're almost done with 21. Nitrosation involves NaNO2 in HCl. Okay, so what does this guy do? So this makes in the beaker or in your round bottom flask HNO2, nitrous acid, which can get protonated eventually to make water. So this should be a little bit familiar. This is a little bit like nitration in 118b. But anytime you make water, it's because water wants to leave. So you can go ahead and boot it off, and all you get is the nitrosyl cation. And the nitrosyl cation is super, super electrophilic. Most nucleophiles will attack this and capture it. So you can think about all the nucleophiles we'll talk about in this chapter, mainly the amines, right? Amines love attacking this thing. So there's usually 3 different groups of amines to understand. The first one is tertiary amines. So imagine if I had TEA and I reacted it with a nitrosyl cation. For the most part, this forms a very unstable N-nitrosamine. Usually just degrades anyways, unless it's like cryogenic. It's not going to survive. If I use a secondary amine, though, we can get a deprotonation, right? We get one deprotonation that can stabilize this N-nitrosamine, and this is a particular, it's a particularly stable compound. I think I read recently, probably in the textbook, that they are cancerous though, so very, very bad for you. But they are stable, right? So that's a possible thing you could predict. Most secondary amines will form this. Okay. Where things get really crazy are in the primary amines. So NH2s. Because when we attack on this N-nitrosamine, sure, we do get an initial deprotonation to stabilize the amine. Okay. But it turns out, eventually, this carbonyl can get protonated. Okay. And then this second proton, which the other 2 amines did not have, right? Can help facilitate another protonation. Okay. And so you form, again, this water molecule that N can go ahead and help kick out. And out comes the N2, the diazo or diazonium. And diazonium, oh my, this is a very reactive compound. In the orgo-2 world that you guys live in, diazonium is the best leaving group in the world, or the best leaving group in that world. It's number 1. Okay. This is the kid that your mom shows you WhatsApp videos of and asks you why you're not them. Okay. N2 is that guy. So N2, incredibly good leaving group, at least on alkyl chains. It's absolutely hard to stop reactions here. You can get SN2s very, very quickly. So if I use some kind of X minus Cl, Br, whatever, to make the nitrosyl cation, that can do an SN2. You could also potentially even get eliminations. That's just how good these are. If you have a secondary center on your diazonium, or even a tertiary, top luck trying to keep these alive. These will instantly ionize into the cation. And I mean, you can imagine cations will do whatever in the world they want to. So I'll just go ahead and draw it on this one here, but you can form the cation almost instantly. And so, I mean, let's say that you're on a center like this, right? That cation is going to, rearrange, do some shenanigans like that. Again, water, Cl, whatever's in solution can capture it. It'll be a matter of concentration. But generally, you find yourself with a lot of mixes, and alkyl diazoniums are not very useful. Okay, outside of intramolecular reaction, not very useful. So what do I mean by that? Let's say that I have this guy here. Maybe some of you guys recognize this. This is glutamic acid. But let's say I have glutamic acid, and I do this NaNO2 reaction, HCl, right? Again, that's going to turn this guy here, I'll show very briefly, just turns into N2+. And again, that N2+ is going to ionize, right? So why is this reaction better than most? Because this is intramolecular, right? We can capture on that cation 1, 2, 3, 4, 5. And a lot better at forming. Okay, this is a much more controlled reaction. You know exactly why is it not erasing. There we go. I realized I was using the wrong tool. But it's a lot better at doing its job and staying a bit more tame, right? Rather than going out and leaving and then leaving the mess for the rest of the solution to deal with. Okay, cool. So alkyl diazoniums, again, not the best, but intramoleculars are pretty good. So if you ever see an alkyl diazonium question, it's usually because you want to do some kind of intramolecular reaction. Okay. outside of this, the best diazoniums are the arene diazoniums, because if you form an arene diazonium, you can hold this at a low temperature, because if this leaves, it forms the phenyl cation, which is not the most unstable thing in the world, but the kinetic barrier to reach this cation is very, very high. You need a high temp usually. So pretty hard to do unless, again, you use some kind of catalyst. So you can capture this end tube long enough that you can be a bit more selective about who you introduce to it. Okay. But with that, that is now all the content for 21. So I think we finished that in about 40 minutes, not too bad. We're gonna have to definitely speed run through 22. So aiming for 30 more minutes on that. I apologize. I didn't want this to be more than an hour, but you know how it is with these reviews. So let me just quickly look at the study guide, make sure I didn't miss anything. Yeah, doesn't look like I missed anything. So we're just gonna keep pushing. We're gonna talk about benzylic positions. The chapter 22, the best way to understand chapter 22 is to realize that we're talking about 3 different benzylic positions. Okay, we're talking about the benzylic position on toluene, so CH3, the benzylic position of phenol, which is OH, and then the benzylic position of NH2, or aniline, which is NH2. That's probably the easiest way to understand these reactions, to kind of segment them. And then this kind of like this phenol section kind of segues into the cope and the Claysons. So that's kind of where those guys come in. That's a bit of a hard one to kind of connect. But anyways, if you have a hard time, again, segmenting or compartmentalizing the information, that's the way to think about it. The first section concerns toluene reactions, or benzylic position of a alkyl chain, and then we talk about phenol and what it can do. Well, really, we talk about how to make these guys, and then we talk about what they can do. Okay, so we'll get right into it. I'm not going to waste too much time on toluene, because that's really the least significant of the information here. Toluene is just interesting in that this benzylic position, right, is this particularly stable, right? If I have a cation here, that cation is stable, right? If I have a radical here, that radical is stable. And if I have an anion here, that anion is stable. So in terms of the anion, right, all we're really saying here is that N-bule can deprotonate that position. N-bule is just a carbon chain. It is 2, 3, 4. It is this here, which is an sp3 carbon. So how is it that an sp3 carbon is able to deprotonate this sp3 carbon? It's because it's benzylic. So it enjoys the resonance of the benzene ring that it's next to. Okay, so usual value you'll see for this is around 40, right? So it's not terribly more acidic, but it's definitely more acidic than this guy, which is around 50. Okay. When we think about radicals, right, radical reactions, there's 2 reactions that come to mind. One is the first reaction we ever talked about in this class, right? The very first reaction we talked about was the radical halogenation, so Br2HV. You can also use NBS here as well. Does not matter. The point is that we're using some kind of brominating agent. And I mean, if you think about this, the NBS reaction should remind you, right? NBS is just that radicalization of that first position there, right? That's really all that is anyways. It's a radicalization of an allylic position is what I meant. I don't know why I said first position. It's the allylic position. So it's the same exact thing. It's just benzylic now. And so we'll go through this radical and we'll get a benzylic bromination. Okay. So this hydrogen here is particularly important, right? We see it now in 2 cases we need that. Another case in which we see the radical being used, right, is when I think about styrene. So styrene is the like the vinyl benzene. This here. And if you guys might remember back in the day, HBr-ROR-HV, right? That gave us the reverse selectivity. So we do go through this radical here, but remember bromine is quote unquote the electrophile here. Hydrogen is sort of the nucleophile. And so that's why we get this weird reverse addition. Okay. So that's all I'm going to really concern you guys about on that. Just understanding these concepts, right? Benzylic is special. So we see some special chemistry on the radical and on the anionic front. On the anion, right, we can capture this with a lot of things. For example, we could capture this with an aldehyde. Sorry, I know when I'm rushing, my drawings get like 20 times worse, right? Which is like, how is that even possible, right? But anyways, actually, let's do it this way. So yeah. So we can capture carbonyls like aldehydes. We can capture epoxides. You could probably do SN2 as well with an RX. I just haven't really seen an example of that before, but you probably can. But these are definitely reactions that can happen, and ones you want to think about are possible, right? Especially this guy here. We'll come back to an example of how we could possibly, utilize an alcohol like this or this for something pretty cool. But anyways, so those are those. And then again, understanding with the radicals, right? Radicals like to form at that benzylic position. And actually, I'll even go ahead and draw an extra carbon here just so you guys can see, right, that difference between going on that carbon next door, which is also a CH2, or I guess the reason why it didn't, right, is because it's not benzylic. Okay, cool. Now, on the cationic front, right, these cations are incredibly stable, right? These are really, really stable cations. So let's say that I have, like a chlorine here, right? That chlorine can ionize really well, especially if it's like secondary, incredibly well. And so we can do sort of SN1 type reactions here, right? Which is not something we usually see occurring, especially if it's primary, right? If it's that's probably the most important one. The fact that this primary reaction can even occur. Okay. Let's use a specific alcohol. Let's do this here. Okay, we'll come back to this benzylic ether. We can also do SN2s, right? Like we don't need to particularly make the cation, but we can do SN2s, and these are always a bit faster than the normal SN2s. Okay, so I could have also have done this as well. Would have given me, pretty much the same product. So let's use something different. Let's say I did this with the sulfur, right? The thiol. The thiol would have worked really, really well here. Okay. We can also, what else can we do with the cation? I'm kind of blanking. I can't think of anything else you can really do with the cation, so we'll call it on that. But those are the three main things to understand about those types of reactions, or about the benzylic position. It stabilizes radical anion cation very well, and so it leads to these special types of reactions. Okay. Now, when we think about the redox reactions on a benzylic position, right? Redox, as long as we have this benzylic H here, right, we can do some interesting chemistry. KMNO4 will absolutely blitz that carbon, destroy it, or anything that chain is, and turn it into a carboxylic acid. Okay, so as long as that H exists, right, we can get this oxidation. So, sorry, I don't know why I erased that. I meant to just erase this up here. So I just want to highlight this hydrogen here. Okay, that hydrogen there is oxidizing that entire, or it's facilitating the oxidation of that entire chain into this carboxylic acid. Okay, and again, it doesn't really matter what it is. It can also be an alkene, right? KMNO4 can also destroy alkenes as well, as long as that benzylic hydrogen exists, right? So cool. So in terms of oxidations, that's possible. Another selective oxidation is the MnO2 oxidation. So a lot of you guys probably remember this from last quarter. There was a question on this in the post lab, but MnO2 will selectively oxidize only the benzylic position or the allylic position, right? But benzylic is the same thing. Okay, cool. Outside of that, I don't really see anything much more else crazy with the oxidations. So we can now talk reductions. Now, the reductions are a little interesting, right? Remember that benzyl ether we made earlier, right? Benzyl ethers can be reduced by H2PD into the toluene. So we're cutting on this side here, sorry, on the benzyl side. It can reduce into the toluene. So I guess I'll do this, and into the alcohol. So you can see where the H is adding. And so this gives birth to the idea that if we can make benzyl ethers relatively easily because of SN2, and they are relatively easily taken off, right, by H2, then benzyl ethers can function as very good protecting groups for various nucleophiles. So for example, I think probably the easiest one to understand is this one here. Let's say that I wanted to do the following Grignard sequence. So I wanted to do MgBr, and then maybe I wanted to turn this into a carboxylic acid. So I wanted to do this, right? So I'm doing Mg, and then I'm doing CO2, right? On paper, this looks great. This looks like it's fine. But keep in mind that MgBr, again, super strong base, it's going to quench on this alcohol. So in fact, actually, this is not what's going to happen. What's going to happen is we're going to get the OMgBr and then the CH. right? So they're going to do acid base. So, we just kind of destroyed a reagent. We've got to start over. So what can I do to prevent this from happening, right? So I can get to my acid here. Well, I can first start with the benzyl chloride. Maybe even a little bit, actually base would be a little tricky here because this could close, but potentially the SN2 could work here. Sorry, the SN1 could work here. So we can get away with that. Right, on paper, for sure it'll work. Okay. And once we have that, actually what we could do here is we could use like a pyridine, right? So a base that only deprotonates once the alcohol adds in. And doesn't deprotonate it before, so we don't get the cyclization. So that's a trick we could do. But anyways, just a thought. But now we can do the MgCO2 sequence, right? Get out the acid and then do H2PD as a very selective reduction to only remove that benzylic ether. Okay. Now, why is it that this is so important again? And another reason why is because ethers generally are very inert. So that's why they make really great solvents and very good predicting groups, because they're super inert. They don't want to react with bases. But usually a normal ether requires extensive heating, extensive hydrolysis, extensive acid, super harsh conditions that will usually destroy other things as well. So, I mean, like, for example, actually, if we did a hydrolysis here, not only will we get this, but you could potentially get a dimerization. This is just a lactic acid, if anything. So yeah, maybe what I wanted to do is make a lactic acid, right? This lactic acid in acid will actually dimerize into this here. So, if I chose to use a much more rigorous, acidic workup, this would not have worked out very well. So H2PD offers a very, softer way, a nicer way of protecting something and then getting it off very easily without, disturbing other groups. We call this an orthogonal protecting group, right? It is a group whose conditions of removal are perpendicular, right? Or are not very, not really a nuisance to any other group on the molecule. Okay. And synthesis, again, usually used as a way to protect alcohols, but don't associate this with alcohols. You can also do this with amines as well. Okay. As you guys will learn, for amino acids, probably one of the best ways to protect amino acids is to turn it into a benzyl ether. So there's a specific group called the CBZ. So CBZCl. It is a benzyl ether essentially. But essentially this. But you can add a CBZ. Oh, wait, no, not CBZ. CBZ is not the... No, that's wrong. What is CBZ? CBZ is the benzoyl group, I think, right? No, I think I'm right. Never mind. I think I'm right. But actually, let me Google it. I'm already looking. If I'm wrong, then I'm wrong. I need to know. No, I was right. I should have trusted myself. Anyways, CBZ is a benzoyl group. A benzyl group. Or actually, what I should say, it's not actually this particular benzyl, but anyways, I'll just use benzyl chloride. But benzyl chloride. So essentially this, and it'll go on the nitrogen first, and then you can do chemistry on this carboxylic acid as you see fit. And once you're done, you just do H2PD to remove that group off the nitrogen, right? So why is that we predict the nitrogen in this case? Very simple. The nitrogen is more nucleophilic than the carboxylic acid in most cases. So it offers a way to, you kind of trick the amine into attacking something that's a protecting group and then allow the carboxylic acid to do chemistry afterwards. So for example, if I wanted to, usually you'd want to do a coupling. So maybe I couple another amino acid here. So I'll call it amino acid 2, right? I'll put A and then an amino acid here, right? And I have my amine here, right? The amine obviously now did not interfere. I can do H2PD, right? Have nothing to worry about now. Cool. Anyways, hopefully that example sticks. If not, it's okay, whatever. But yeah, so the benzyl group is very good protecting group. And you can use it on a variety of nucleophiles. I imagine if it shows up on the exam, predict the products type, or it'll be some kind of predict the products, or it'll be some kind of like in synthesis, like the protected alcohol or something, or maybe even explanation, right? Cool. All right. All that I'll leave on that is that just keep in mind that with the benzyl group, look out for like nitriles and alkenes and alkynes, right? Look out for, I'll put X here. X could be C or N, right? And just look out for that because those will reduce. Okay, so cool. All right, or I guess double bonds too. So, but yeah, cool. All right, so that's the benzyl ether reduction. The last reduction is the Birch reduction, and then we'll get into the meat of this chapter. Birch reduction is pretty simple for the most part. You're essentially adding a single electron into the system. So NA's solvent and NH3 liquid, and usually in ethanol as well. All you're really doing is when you put these two things together, Na and NH3, you're making basically electron Kool-Aid or electron juice. And so electrons are kind of floating freely in solution, kind of interesting to think about. So it'd probably really zap you if you put your finger in it, right? But these electrons are essentially adding into the ring. So you can imagine you're kind of adding it into the ring. A couple different ways you can draw it, but that's just one way of doing it. And what you're forming are these radical anion species. Okay, so this is a radical anion. Okay, now this radical anion, you can imagine just back in 118b when we did this on alkynes, right? These guys don't like to be next to each other, so for the most part, right, they'll separate. Right, form this here. And then the anion will protonate. Usually, I mean, there's ethanol in solution, so ethanol will do it. And then we just do the same thing over again. So we add an electron into the system, and then we just protonate. Okay. And there you have it. That is your Birch reduction. So these are commonly viewed as dearomatization of arenes. So for example, you can imagine if you did this on like an anthracene or a naphthalene, right? Naphthalene will just reduce into, two non-aromatic dienes, or I guess it's like a triene, right? Because it's together. But hopefully you see my point, right? Whether double bond is here or here, it's the same thing. But yeah, it just dearomatizes the benzene ring. Where really the Birch matters is in substituent effects, right? When we have things on the ring. And so I know a lot of people are having difficulty understanding this, and to be honest, everyone kind of does. Even Arthur Birch, the man who developed this reaction, couldn't even correctly predict what the mechanism of this was. So don't expect to understand all of it immediately. But for the most part, the idea is simply this: for electron withdrawing groups, when you add the electron in. Now I'm going to draw some arrows, and they might piss some people off. It doesn't really matter. Just have to understand the idea. Okay. But the idea is that when the electron inserts into the ring, what you form is a radical cation, a radical anion. So something like this, where at some point in this radical anion, there would be a proton capture. So we call this the first protonation in the Birch mechanism. Turns out the first protonation, more times often than none, occurs initially para. Okay. So this is just what happens. It just turns out that this is what it's going to be. Okay. They've done many kinetic studies on this. Actually, Birch himself was really upset about this. He thought it was something else. He thought the anion would capture or ipso, so right on the EWG, but it turns out EWG, the first protonation is para. Okay. And so you can kind of see how these arrows might suggest that. Most literature will avoid this topic just by drawing dotted lines, a radical and an anion in the middle, and then just showing that the first protonation happened para, just because it's so annoying to have to deal with. Okay, but then you can imagine, right? You can imagine this will combine to make another radical, another anion, and then quench again to make another proton. Okay, so that is the general gist and idea of the Birch mechanism for EWGs. And so the big thing to take away is that sp3 carbons are where you want to have your EWGs land up in the end. So you can imagine with EDGs, then it's going to be slightly different, or not, completely opposite, right? Again, we're going to sort of insert an electron into the system. We're going to form a radical anion, but obviously we have to show something, right? We have to show why we're seeing our protonation. Generally speaking, the protonation that we see is going to be on the ortho position. So it turns out that this is the dominant radical anion. And so this is what gets initially protonated. That first protonation is on the ortho position. Now, the way that I kind of reconcile this to make it make sense, because again, I'm not a mechanistic, I'm not a kinetic guy, I don't really care. But a way to kind of reconcile why this makes sense, if you think about in the EWG benzene, the carbon that's probably the most electrophilic is the one that holds the EWG. So the electron can insert here, and the electrons can kind of dance around, so you can form this radical anion here. For the EWG, you might remember, sorry, the EDG, you might remember from EAS, the ortho para positions on EAS are very electron rich, right? So the meta positions are actually very electron poor. So you can imagine a sequence where an electron adds in here, and then electrons kind of move to form an ortho anion. And so that's how you can reconcile why we see the movements that we do. Just to help it make sense, right? But again, no one really knows how this works just quite yet, so neither can you guys really know either. These are just tools to help you understand it, okay? But again, this will turn to radical anion, and then we'll get the protonation here. So generally, sp2 carbons are where you want your EWGs, okay? So just a reminder, it's easier to remember all the EDGs, and then you'll know all the, sorry, this would be EDG, and then you'll know all the EWGs. EDGs are generally R groups, amines with lone pairs, and then oxygens, right, with lone pairs, as long as they're directly connected to the benzene. So you can imagine, right, you can imagine having like an ester and like a nitrile, for example, right? When I do my Birch reduction here, I just want to make sure both groups are satisfied. So probably the easiest thing to do is to, again, de-aromatize the ring. So just get rid of those pi bonds for a second. And then, because the EDG is what wants the pi bond, you can start there. So I would either draw a pi bond here or here. Remember, the pi bonds are de-aromatized, so they're always going to be opposite from each other. So this pi bond will be opposite from this one. So this is one possible combination, right? The other possible, oh, you know what? I chose the hardest one to begin with. So let me actually change this. We'll talk about what I just drew in a second. But I realized I accidentally drew like the hardest one. But anyways, we can draw this pi bond here and this one here, or we can draw this one here and this one here. And you can see this one's the best because it puts the EWG on the sp3. So this is where it works. We could even then think about this in an ortho kind of way and think, okay, how would this work if it were ortho, right? Again, get rid of the pi bonds, draw out your ester. Nitrile, okay? I can draw a pi bond here and across from there is that, or from here across there is that. Clearly, this one is better, right? Because it puts, again, the EWG on the sp3. So that works out very well. Okay. Now, the one that I just showed that I was like, oh, this is kind of a tricky one. When it's para, obviously, you can't really draw an example where both are satisfied, right? Because either you have the pi bond, satisfying the EDG in this case, or in this case, or you don't satisfy it at all. Generally speaking, because we're adding an electron into the system, and we're forming an a radical anion, the anion stability is usually what's most important. And so because of that, you might see you will see a tendency to get the 1,4 diene where the EWG is satisfied and the EDG is not. But this generally leads to mixes. It's a bit complicated, so you won't see it on an exam, but it is a good one to think about, right? I mean, if you can solve this problem, maybe Birch might, dig himself out of his grave and write a paper with you. But this one generally is kind of the one that sucks. Okay, cool. Now, you don't always need to have a mixed example where you have an EDG and an EWG. You could always have, the same example. And so the easiest way to convey these kind of examples is to kind of just put 3 things on a ring together and just de-aromatize it and see what we can, see what happens. So if I de-aromatize this ring, again, I'm just gonna kind of toss the pi bonds on one side. So we can either get this. This is absolutely the worst one, right? Because everything is given sp2 when it wants sp3. But we can do this here. And now you can kind of see 3 different things, right? One thing you can see is that the para-para is always the best because they can both be sp2. So this is the happiest of the relationships, right? The para-para relationship. The para-meta is not the happiest because, you know, one thing is sp2, one thing is sp3. Same thing with the ortho, but you know, it's kind of unavoidable. So with this one example, you kind of get 3 in one. Hopefully you can see that, right? You get the para, you get the meta, and the ortho, right? The cool thing about EDGs is that if you were to do this sort of same experiment, right, where you put something ortho, meta, and para, and you kind of compared all those 3 different relationships, you'll realize, and I'll just kind of draw it now just for sake of time, everything can be satisfied and be very, very happy. Okay, so everything is super, super happy about this, super stoked. Okay, cool. All right, so that is the Birch reduction. The only cool thing I'll leave you with the Birch reduction is that whenever you do a Birch reduction on methoxys or anisols, what you tend to get if you hydrolyze these are enones. So you tend to form enones. So this pi bond will isomerize essentially. So cool little, I don't know. I would only worry about this if you saw this in lecture, but that's just something, it's something that I've seen in literature. I think I might have seen in your textbook too. Okay. Cool. All right. So that's the Birch reduction. All we're going to talk about for that. Finally, now we can get almost an hour and change later, get into the meat of this exam, the SNAR reactions, the NAS reactions, how we make phenols and how we make anilines. I imagine this is the reaction that's, you know, giving you guys the hardest of time, or at least as though, you know, where it really feels like you've learned a million things at once. But don't worry, again, we always have ways of predicting these or understanding these in simpler ways. It's the whole point of me, you know, having studied all this material. Okay. But let's get into it. How do we make phenols and anilines, right? What do we do with these guys? Or how do we make these guys? Well, there is one way already for both on how to make them. So that's a good thing to have on your note card or a good thing to have in your brain. You can nitrate a benzene, HNO3, H2SO4, and then we just talked about this, right? The reduction sequence. You can do a reduction to give you an NH2. So anilines, we already knew how to make in one way, right? Phenols, right? We can do an acylation. And then we can do MCPBA. Right. And then remember, hydrolysis of this, whatever you want, right? That will give you the phenol. So we kind of already have a couple ways, or really one way each right now, on how to make the phenol or the aniline. Okay. But these require electrophiles, right? So these require benzenes that are usually very electron rich, especially for the Fredo-Crafts pathway, right? This won't even work if the ring is even slightly deactivated, right? If there's like a NO2 here, good luck even trying to do this, right? This is going to be near impossible to take care of. So generally speaking, these pathways are, you know, I mean, an orgo 2 ways to do these, or ways to make these is totally possible. But we have other ways of doing these that are a bit more reliable. And these are our substitution reactions. Now, if we just think about substitution in general, right? Substitution is we take an electrophile, we add a nucleophile, and the nucleophile kind of substitutes it out, right? So that's essentially the idea. So if I wanted to apply this on the benzene front, I would just take a benzene, I would stick a chlorine on it, and then I would kind of just throw OH minus at it. Now, if I just did this, nothing happens, right? Because again, you can't really do SN2 on an sp2 center, which is what this chlorine is on. So tough out of luck there. But maybe what I do is I heat this up a little bit, like super, super high, 300 degrees maybe, and I jack up the pressure in there, right? I make it, you know, very, very highly pressurized. Turns out we slowly get some reaction. Okay, so we will slowly get out a phenol. That's crazy. So it looks like substitution is working, and almost to me looks like it's just, you know, joining on and kicking off. So maybe we lied to you guys. Maybe SN2 can work. Okay. Now, if I take a substituted benzene or aryl benzene, and I do this reaction again, maybe this time I use NH2 minus because it's a bit more basic. So, you know, I don't have to really be too rigorous with it. It's already willing to attack things. I do get a substitution. But it turns out I also get another product. I get a meta product. So not only am I now substituting on the same position, but I'm also substituting next door, right? So whatever is the intermediate responsible for the substitution spans 2 carbons. Only very few reactions or very few function groups that can do that span 2 carbons, right? Take a guess, right? Maybe there's a bunch of them in the ring, but sort of what's the saying? The nail in the coffin is if you try to generate this intermediate. So let's say I take N-butene just to generate this intermediate, whatever this is, okay? And I introduce to this intermediate a diene, so furan, for example. What I get is this here, which some of you recognize. This is a Diels-Alder adduct, okay? So what in the world is going on? Well, if this is a diene and the benzene is forming a dienophile, I mean, we know what dienophiles are. They are pi bonds. So the intermediate for all these reactions is going to be the benzyne. It's going to be the benzyne pi bond. Okay. So how does this work? Right? Very quickly, the way this reaction works is you have these protons here, right? That when you heat this up, at least in OH minus, right, base can be promoted to, it kind of depends on who you talk to, right? The mechanism that I tend to see floating around is something like this. You form an anion, and then the anion kicks off the Cl, and that forms the benzyne. And so the benzyne, right, is an electrophile possibly at either these 2 positions. And so OH minus can initially attack here or here, right? At least in this case, it doesn't really matter, right? Because we'll get the OH minus with the anion, and that will quench on water or whatever protic solvent you have in solution to get out the phenol, right? And so you guys might remember there were those, you might have talked about the test in class where if you tag the carbon that the chlorine is on, right? Or yeah, the phenol is like 50% of the time on that carbon, 50% of the time not on that carbon, right? It's right next door. So possibility there, or like a type of explanation or something to know. Okay. You can also do this with amines as well. Amines will also do this reaction, right? Generally, right, when we have the alkyl substitutions, all you have to be wary of is the fact that we can add either position. So if I have, for example, this here, right, I'm going to just condense some arrows here real quick just to get through this really quickly. Okay, because I can do that, right? I've already passed the class. But NH2 minus, right, can either attack here or here, which results in the benzyne mix, right? The meta para mix. Or the ipso-ortho product, right? Because we're either adding ipso, same carbon, or ortho to that carbon. Okay. Now, the degree to which alkyl chains matter is just that they tend to form mixtures. You might have an example where the alkyl chain is like closer, and that can, to some extent, exert some sterics. For example, OH minus, right, might be more motivated to take this proton here. Oh, sorry, not NH2, chlorine. Right, so we'll form this here. And again, we'll get the 2 products. If I draw a line like this, that means that the OH is on either of these 2 carbons here. I'm just, again, getting a little lazy on drawing things. So OH is on either of those 2 carbons, right? This one or this one. Okay, so that's a possibility. If it's like right next door, obviously the chlorine has no choice but to be eliminated on this side. Actually, we didn't even draw this. So this is actually an acceptable resonance form, right, where 3 pi bonds are kind of stacked on each other. It looks kind of weird, but it's totally possible. And again, there is a bit of sterics involved with the ortho product, so you might have a bit of a meta dominance there. But I think for the most part, the vibe that I was getting from this class is that you'd want to write both. So actually, I'll just do this. Yeah, so tend to get mixes. Okay. Now, where things get a little interesting is when you have groups like CF3. So I'll draw one example of this just because if it shows up, it'll probably just be this example. But if you were to do this elimination here, right, CF3, it turns out CF3 being an inductive withdrawing group, right, can inductively pull on this pi bond make it so that's more positive on the left than on the right, or you can see where the positive sort of lines up. So your nucleophile, right, tends to add more often than not to the meta position. Okay. So that's a good example to know. Okay. Other groups that can do this are like OCH3 or nitrogen, right? Anything that's inductively withdrawing can do this, honestly. So even an NO2 can do this too. So I'll just put some groups. Cool. All right. But that's the benzyne, and as you can see, it's a very rigorous reaction. Not the best, not the one that you want to go to immediately when doing these. So instead of doing benzyne, what you can do is a SNAR. And so the setup for a SNAR is, and I'm going to kind of, sorry, I have to start speeding through this because we're about to hit the 2-hour mark on just reviewing, which is what didn't want happening. That's okay. But HNO3H2SO4, FeBr3Br2, right? We can brominate. Bromine is an orthopara director, so our first direction goes para. We'll get the NO2. And now that we have this NO2 here, right, this NO2 allows us to do very, very weak reactions. So when I'm sorry, very, very mild reactions is what I meant to say, right? And so we can get these really nice SN2 type, or sorry, SN type reactions, okay? So what's going on here, right? What is this NO2 facilitating that wasn't being facilitated in the previous example? Well, when we have an EWG like NO2, right, ortho or para, so it could have been here too, to this bromide, right? The nucleophile can enter and the electrons can sort of be shot into the EWG. Okay. So I kind of think of NO2s or like nitriles or, so yeah, NO2s, nitriles, carbonyls. These are all groups that are resonance withdrawing, and they're all capable of doing SNAR to some extent because they can, take up electrons. They're sort of like an electron vacuum. One little joke I like to make is that NO2 is sort of like the Dyson Airmaster of the SNAR reaction category, right? Because when it's ortho or para to the leaving group, right, the nucleophile can add in, electrons kind of shoot in, right, and they're stabilizer, willing to have been displaced. Now, obviously, this is not the most stable form of this molecule. So these electrons can shoot back out, but instead of kicking out the nucleophile this time, what they kick out is the leaving group, so bromine. And so we can get much milder substitutions with that. Okay, so that is the SNAR mechanism. And again, any resonance withdrawing group can do this, right? You can imagine if I had a ketone and I did, let's say, NaCN, guess what? We'll get the CN here in place of the ketone, sorry, of the chlorine. And the ketone is what facilitates the SNAR because it is ortho and para, or ortho or para. Another quite often question that I get is, do I need to have a million of these NO2s or ketones to do this? No, not really. In fact, I've actually done a SNAR on probably what is the weakest of the withdrawing groups, which is an amide. And I did it with one of them. Granted, I did have to heat it up a little bit, so it's not the easiest reaction. I had to heat it up, but it still works. So I did something very similar to this at my time at Davis. So this reaction definitely works. Again, do have to heat it up just a little bit, but it's a SNAR if I've seen one, right? And it's that para withdrawing group that allows that to happen. Okay. Cool. So let's say that I have, oh, actually, there's a question on this, so we'll go over that when we get up that. But generally speaking, right, the Q for a SNAR, right, is having some kind of EWG that's resonance EWG that is ortho or para, right, to a halogen, usually a bromide, actually usually a chloride. So one little niche fact that I'll kind of throw out there: the order of reaction for SNAR, or the order of leaving group ability for SNAR, is actually reversed. I don't really want to get into it. So if you want to know, you can ask me in the chat. I can tell you, but this is the order for SNAR. Okay. But anyways, EWGs, ortho or para, kind of give away this reaction. And again, way better than SNAR, right? sorry, way better than benzyne. Like if I had a chlorine here that's meta to everything, so it has to go by benzyne, this guy's reacting first. So this guy would react first by SNAR, right? And then maybe this guy reacts by benzyne. And that's only if we have rigorous enough conditions for it. Okay. Cool. All right. So that's the benzyne and the SNAR. The last two reactions we have to cover for this sequence are the PD and the nitrosyl. So again, NO2 you can reduce into NH2. And then NH2, we can do that NaNO2 thing, right, at a very low temperature. And what we can get out is the N2 plus cation, the diazonium cation, which can be replaced by a lot of things. H3PO2 will essentially remove it, turn it into H. The Sandmeyer reactions are the reactions where you see copper salts. So CuCN and NaCN, or CuBr, NaBr, right? Anytime you see that Cu, you know it's a Sandmeyer, but all of it's just the same. I know you guys went over a very rudimentary, like very, very like bare bones mechanism for this. And you know, I mean, to be quite honest with you guys, it's really hard to write mechanisms for catalytic cycles. I mean, metals and stuff. So what you guys have is kind of like the bare minimum. So don't stress too much about that. It wasn't too much either. It was mainly just that the copper, you know, again, inserts an electron. N2 is lost, and you have the radical, and the radical interacts with the nucleophile, quote unquote, right? But yeah. So usually whatever's after the arrow is, you know, what you want, or it's a product that you know, the nucleophile you want to use to attack. If you do a hydrolysis at a high enough temp, right? So even if this is like 100, or even at like 50, or even 30 room temp, right? This will just turn to a phenol. Okay. What is probably the most interesting reaction is the diazonium coupling, which is if you take a phenol or an aniline and you react it with these N2 compounds, they actually make these diazo. This makes this azo di. So basically, the para position always attacks because it's, you know, the least sterically hindered, least deactivated, right? So you form these. Generally speaking, oh, sorry. I'll put this here. So generally speaking, actually, let's do this. Generally speaking, when you want to figure out what two things made your diazo, or so your azo di, the EWG is usually on the azo group. So usually the EWG is on the azo group to make it a better electrophile. And the EDG is on the nucleophile, so it doesn't have the azo on it. So this is a way to effectively cut it, because we see the EDG here and we see the EWG down there. Okay, cool. Outside of that, that's about it. It's a really cool way, again, to kind of make these bonds. You could also, I suppose you could also substitute this for amines, but you started with an amine, so why not just do a reductive amination if you want to put a, like for example, if I wanted to turn this into like this amine here, right? Just do a reductive amination. You don't need to go through the process of diazotization. Okay, cool. So you can imagine this sequence back here that I did for the SNAR, you could have actually detracted, you could have diazode the NO2 and then replace it whatever you want. So like, for example, a BR again, or like an OH. That's probably the most important thing, right? Cool. All right. Again, sake of time, I've kind of got to speed through this because we're really, really behind right now. I apologize. Last thing is the PD coupling. PD coupling is a bit of a cheat code. Essentially what you do is you take an aryl bromide, no conditions required, no nothing. So you don't need EWGs, you don't need strong bases, you don't need NO2s. You just need PD in a nucleophile. And the PD facilitates a swap, basically. It just substitutes, and that's it. So it's like what I call this the Konami code, or like the cheat code. Because if you're ever stuck and you just need to figure out how to substitute something, you can try doing that. It will work, again, like 99% of the time. But I will tell you guys that a very common test exam sequence is usually going through the bromide into the NO2 And then I won't draw this out because I don't have time to do this, but usually what you'll do is you'll do some kind of SNAR on the Br side, and then you'll do a diazo on the NO2 side to completely change the identity of this. So there's many ways you can do this. You can test yourself and try whatever you want, but this is a very common test sequence. So study this, understand it. I mean, there's a reason why I showed it, right? Is so that you'd be prepared to see that. Cool. But with that being said, we're done with the preparations and all we need to know. One last thing that I will say is just that when you're thinking about synthesis, benzyne should be your last chance or your last thing. Don't start with a benzyne. I would try to start with diazo. I would try to do a diazo or a PD, or unless it's set up for a SNAR, do a SNAR. Okay. So again, looking for those key things, like a SNAR needs the para NO2, diazo just needs an NO2, right? And then PD is your cheat code. Cool. All right. So let's get into phenol reactions. Just going to kind of condense them onto a page here because I don't really want to think about them too much or talk about them too much. For the most part, you can take a phenol and you can methylate it. I think you guys need to know, or yeah, alkylate it, or yeah, you can do this, or you can do this. Right. So the oxygen is always a better nucleophile than the benzene ring in majority of cases. This is what we tend to see usually. So this O acylation and O alkylation. But some kind of interesting reactions are the ones that happen on the benzene ring, even when we have an OH. So for example, the Kolbe-Schmidt, that's NaOH CO2. Kolbe-Schmidt always gives us a salicyl acid. So it gives us the ortho acid. Very good reason for this is because the Na, that metal, does what we call an orthometallation. It has an orthometallation interaction. The Na kind of binds the OH and the CO2 so that it's closer to the ortho position, and so that it forces it to, be mostly ortho. On the exam, I mean, this is definitely kinetically controlled. So on the exam, you should definitely expect that. Okay, that would be the kinetic product. Okay, and the only product for the most part. Okay, there's also the hydroxymethylations, which involve just like NaOH, formaldehyde, and heat. And these guys will form initially. So we'll go through this anion here. So if you want to write this down, you totally can. I just don't have the time or the space, but you'll form the phenol enolate, which will turn into the keto enolate, and this will go out and attack formaldehydes. Okay, and essentially form these compounds here. Okay, which upon heating, which we see here, will form the quinone methide. Okay, you can form this ortho and para. Okay, now all you really need to know for the quinone methides, for the most part, is that one is that they're formed by the enol form. So they're formed by the enol form of the phenol, and they're particularly, what it really is it's like a benzylic position, right? This benzylic, it's like a benzylic position kind of, right? Like if I draw the tautomer of this, hopefully you can see how this would work, right? It's sort of like a benzylic position, and it's activated, right? It's activated for elimination because we get these quinone methides. Okay, now you can form them on the ortho and para positions. Generally, the nucleophile though that captures these is the phenoxide in solution. So you'll form what we call phenolic resins, plastics basically, but these guys are the ones that usually do the capturing. And so the main point to take away with the phenolic resins is that you get these beautiful polymers that always have an orthopara relationship between each other. So the OHs, when you compare their connections or the connections on the ring, they're always orthopara. So you can kind of get the idea here, hopefully, right? Always orthopara. So if there's ever a question on which phenolic resin doesn't make sense or is incorrect, or which bond is incorrect, you're looking for the one that's like this, right? You're looking for the one where it's like meta to the OH, right? There should never really be a meta OH relationship. It should always be orthopara. Okay, so every phenolic resin, just look out for that. Okay, but there really isn't any other kind of nucleophile you tend to add into these things. That's usually about it. Okay, cool. Now I'm going to quickly jump over to the just very quickly going to jump over to the oxidations. So I can start with this diphenol, and a lot of things can do it. Ag2O, Jones, whatever you want. These guys can oxidize to quinones. Quinones essentially are two Michael components put together. They're also very good oxidizing agents, but that's beyond the point. If you have a nucleophile, they will Michael add into any of these four positions. If one is not available, obviously it won't go there. But basically go back to the diphenol, or yeah, the diphenol, the bisphenol, and the nucleophile will be at one of those four positions. Okay. You can also then do Diels-Alders, right? Like you can introduce dienes, and that will give you, right? You can usually, if it's done low enough, right, like a very low temperature, right, you can usually capture at the capture on the quinone. But I mean, this thing is like 2 coughs away from turning into, a phenol. So if you just heat this up, HCl turns back into the diphenol. Okay. So very common sequence this one is. I'll throw in these methyls just so you can kind of track what's going on there. Okay, cool. But in terms of quinones, I'm pretty sure that's about it on the quinone front. Let me just check real quick. Oh, actually, there is nothing about quinones on here. Oh, there's just oxidation. Okay. So just know the oxidation, I guess. So all that leaves us with then is the rearrangements. Finally, right? Finally, we're almost done. The rearrangements, which you initially first discuss on the phenol, but I'm kind of doing things out of order. The rearrangements, the easier one to talk about is the Claisen. So the Claisen is it's an allyl vinyl. So this is allyl and this is vinyl. It's an allyl vinyl ether reaction where when you heat this thing, what you get out is a gamma delta unsaturated carbonyl. Okay. So this is what we call a sigmatropic reaction. It's completely orbital driven. And also driven by the fact that we turn 2 CC pi bonds into a CC pi bond and a CO pi bond. CO pi bond being significantly stronger. So this is the driving force of this reaction. Now, one way that I like to explain this reaction or view it, if you draw it a particular way, right, is that this reaction is essentially a mirror. So what I mean by that is the electrons are moving in a circle, but essentially the shape kind of mirrors itself. So this is what I mean. So if I were to redraw the Claisen on the side here, if I want to draw what this looks like on this side, you're doing basically 3 simple moves. You are bonding this back, so let's actually start with this. Oh, I knew it would do that. Okay. So let me redraw this. Okay, cool. So what you do first is you break the vertical bond. So that bond there, you form it in the back. So you move that to the back. And then these 2 pi bonds move up. So they move to the left. Okay. And that is how you draw the mirror here. Okay. Now, if I kind of get rid of the oxygen here, again, you can kind of see, hopefully you can kind of see what I mean by it's a mirror, right? It looks like it's exactly just, it's like it's flipping over, right? This is flipping over to this, right? The only thing is that the oxygen's here to help us keep track of what's actually happening, right? It's not exactly flipping over in this case, but it also helps us track, right, where all the atoms go. So 1, 2, 3, 4, 5, 6. If I count it like that, then the oxygen should be 3, right? This would be 2, this would be 4, 5, 6, 1. Okay. So if you have a method of flipping it, whatever your method is, just choose one, right? Whatever your method is. This is just my method, so you're totally welcome to use it. All you have to do now is just number things, okay? So in this numbering instance, I have the vinyl side as 1 and 2, or I have the oxygen as 3. So on here, that just means that I'm counting 1, 2, 3, 4, 5, 6, making sure the oxygen ends at 3. So let's say that I have a complicated example of this, where it's not just, easily choreographed as such. How can I solve a problem like this? And we'll do probably 2 examples, okay? So let's say that I have something like this. Okay, so I made sure not to be easy on this one. Okay, cool. Again, how do I recognize that this is a Claisen? Well, one way you can recognize is that you see there's only heat. That's a very easy way to recognize that. Another way is, again, look for that vinyl component and that allyl component to that oxygen. Okay. You can also do this. You can count from the pi bond to pi bond, one end to the other. 1, 2, 3, 4, 5, 6. There'll always be 6 carbons. Okay. Cool. Now, again, I can draw my stencil, which I'll do it again just for the purpose of doing it again. And I highly encourage you guys to do it too. Again, I draw mine like this. Okay. Okay. But I'm going to go ahead and number this from the, looks like this side is the allyl side, right? Versus the vinyl side. So 1, 2, 3, 4, 5, and 6. This is going to be 4. So I want to start from the allyl side. This is vinyl. This is allyl. So 1, 2, 3. Oxygen's at 4, 5, 6. I know I did this right. Okay. So I can go ahead. I know it's going to look like something like that. But just to get the mirror down correctly, right? I'm just going to go ahead. I'm going to redraw this as such. And then I'm going to repeat those 3 steps. Get rid of the vertical bond and put it in the back, right? And then move the 2 pi bonds up. Okay. And there you go. And again, the numbering stays the same. So if this oxygen is 4, right, this is still 5, 6, 1, 2, and 3. Okay. Now let's just put stuff where it needs to go. 1 has an ethyl, so that would be here or here, right? 2 has a methyl, so that would be here or here. 3 has a carbonyl on it, so that would be here or here. Okay. 4 has an oxygen. 5 has a methyl, so that'd be here, or 6 has an ethyl, that would be here and here. And there you have it. That is your Cope rearrangement, or sorry, Claisen rearrangement. Okay. So sake of time, we'll only do one, but hopefully that, it kind of shows you what you need to do there. The only one that's significant outside of that is the Cope that you can do, Claisen you can do, sorry, with phenols, because phenols are vinyl already. So what you can do is NaH and then add in an allyl component so that you get this here. Okay. And then heating this will go, right? First, it'll form this here, but this will tautomerize back into the phenol. So normally, again, we do form the ketone, but in this case, we don't. So what's a very easy way that we can do this without really drawing anything out? Here's the tip. So if you label the bromide from Br as 1, 2, and 3, when you attach it to phenol, this is 1, 2, and 3. When it rearranges, it's 3, 2, and 1. 3, 2, and 1. So if I put stuff here and here, right? 2 has a methyl, that would go here. 3 has an ethyl and a methyl, right? I just kind of copy that over, right? Just make sure you don't just literally move this down, right? 1 is actually going to, oh, sorry. No. This is, oh, yeah. Am I, oh, I read these numbers wrong. Sorry. That's what I get for rushing. But 3 has the ethyl and the methyl. 2 has the methyl and 1 has nothing. Okay. So that would just be the same here. Okay. Cool. So that is how you can very quickly do your Claisens. And I'll leave it at that. All that's left now is the Cope, which is the carbon variant. And so this one's always, again, a bit harder to see in a predictor products, but it's very easy to see the flip though, because it's literally just a mirror. Right? You're literally just mirroring this over. It's like you're flipping it over, but the numbers stay in the same spot. So if this is 1, 2, 3, 4, 5, and 6, right? Then this is 1, right? This is not 1. This is 1, 2, 3, 4, 5, and 6. So depending on what's on there, right? Usually Copes are more in equilibrium because neither side has a driving force. A very good driving force, though, can be something like an alcohol. For example, something like this. Because when I play the alcohol where it's supposed to be at 3, right, this is going to tautomerize into a ketone, right? So this is a very good driving force for this reaction. Anything that can, reduce the energy of the system, release any stress, whatever it can to make the system more stable, Cope will then be generally out of equilibrium and pushed towards one side. Okay, but generally in equilibrium. Okay, cool. But with that being said, finally we are done. I think it took us 2 hours to get through that. So again, I apologize. Kind of had to speed run through it. Hopefully we got through most of the material. But with that, now we can get into the actual exam. Finally, right? What we all came for. And again, obviously the reviews are for people that need it. You don't have to watch it. You're not forced to. Cool. All right. So with that, we can now go through the predictive products and talk about what we need to know. Hopefully, again, you guys try these out on your own. These are very, I wrote the first exam to be very, very simple. Just if you knew the concepts, you should get most of these right. And you should fare very well on these questions. Cool. So looking at the first example, I have a nitrated benzene and a chlorobenzene. So, nitros and chlorines and nucleophiles. I'm thinking some kind of substitution. So off the bat, I'm thinking, SNAR or benzyne, right? Maybe, I mean, I can write it down N2 plus, right? Because there is NH2, NO2. So remember, what are the things that give away these reactions, right? NO2 will require that I have N2 would require that I have an NO2 plus, NH2 plus NaNO2, right? So I'd have to go through this pathway, but I don't see that anywhere here, so I'm not at all worried about that. SNAR will require some kind of halobenzene that is ortho or para to some kind of EWG, right? And so I do see a little bit of that action here, right? I do see a chlorine that is ortho para to two of these NO2s. Benzyne is usually any other arine, right? So any other arine with a very rigorous condition, right? And if there's a group, if it's an alkyl chain, it can be wherever. If it's like a withdrawing group, it'd be like meta. Okay, but this is usually very rigorous, requires very strong nucleophiles. So like R minuses, N minuses, O minus with a lot of heat, right? Very, very rigorous. And so when I kind of look here, I do see a chlorine that's meta to two of these NO2s. So maybe there's a benzyne possible here. But remember, SNAR is easier than benzyne. So if you think that a SNAR is possible, that's probably what's going to be the main reaction. Benzyne would, again, require, I mean, the SNAR would happen first, benzyne would happen second, but only if the conditions allow us to. When I look at the conditions, I do not see an N minus. That's an NH, not an N minus. I don't see an OH minus with heat, and I don't see like a Grignard. So absolutely, benzyne's not possible here, right? It's not rigorous enough, not enough tension on the system. So definitely going to be a SNAR. And again, remember, SNAR is going to be the one that is orthopara to the NO2. So between A and B, it's going to be this guy that reacts A. Right. And morpholine reacts because, again, it's NH. That's more nucleophilic than the NO, the O. Okay. Get this here. This chlorine just hangs out the whole time. Okay. So very, very common question, very, very common question to see if you conceptually understand SNAR, right? And conceptually understand how to rank the other substitution patterns against each other, right? I mean, if I didn't have chlorine A, right, we could still have a reaction, right? So we can write this down. We can still have a reaction. It's just got to be super rigorous. So for example, it would have to be like NH minus, right? NH2. So it'd have to be something like this. And then we can get, right, a benzyne. Although this benzyne will be a bit difficult to predict because technically you can get two products, right? Because of the, I mean, let's just say you took this H here, right? The N could also be here too. So it's a bit tricky, right? Because you guys didn't really talk about substituent effects, but potentially, right, we could have an amine here. Actually, let's even just do, let's just do NaNH2, just for sake of simplicity. Okay. So we could have had a benzyne if that chlorine A didn't exist, but I mean, do we really want it though? It's kind of a sucks as a reaction. Okay, cool. So that's the first one. You can imagine a lot of nucleophiles can replace this, like CN minus, OH minus, right? OR minus, right? I mean, even enolates, actually. That's not something we talk about very often, but enolates could also potentially serve as a nucleophile in these reactions. Okay, cool. All right. Moving on to B. Look at that. We have an aryl benzene. We have a nucleophile, OH minus. So I'm thinking again, some kind of either SNAR or benzyne or N2 plus. I mean, SNAR can't be possible. There's absolutely, I mean, when we look at the chlorine, ortho, and para, no electron withdrawing groups, so SNAR is impossible here. N2 requires, again, an NH2, so we don't see that either. And I don't see NaNH2, NaNO2 anywhere on the line. So there's definitely going to be a benzyne here. And you can tell because of that highly rigorous condition. And so remember, for benzyne, we're going to get an alkyne. Okay. Now, again, when we think about which proton here is more likely to get taken, it would probably take this one more often than not, because this proton is very sterically hindered because of that ring. So much more likely that we'll get the benzyne here. But that means that we'll get a chlorine on either side here. Sorry, I know I've been writing this. It's just because it's convenient, but I'll go ahead and write the two products. Right, these are very much the likely products. So you can see that when it comes to benzyne, if you think there's two products, guessing the para-meta product is very, very good. It'll get you through majority of problems. Okay, cool. Only way this could work in any other fashion is I have to do some kind of like nitration here, or some kind of Friedel-Crafts here to get on Oh, actually, it wouldn't even go there. It would go here. Sorry. So some kind of nitration, some kind of acylation to get a withdrawing group on that position. And then maybe I can do a SNAR. That's totally possible. So maybe first step I do this. Right. And then second step I do like, oh, sorry, not chlorines, OHs. Right. Maybe I do OH minus again. Right. And then I only get this product. Right. I only get that product. Or I do like NH3, like ammonia, and I get the aniline at that position. Right. Only that one position. Right. Possibilities, things to think about. Okay. Hey, imagine if I did this. What if I did KMNO4 first? Right. If I did KMNO4 first, right, that would give me the diacid, which again, now I have, looks like in a para withdrawing group. So I could also facilitate SNAR that way too. Okay. So again, any kind of electron withdrawing group that's by resonance, that works. Okay. That usually works. Cool. All right. Moving on to C now. What we have is an amine. We have excess CH3I. I guess you can see a base here. I just didn't write it in. We have OH minus. So this is clearly a Hoffman. Remember, with Hoffman, it's super simple. Just dot your alpha carbons. So mark your alpha carbons. That's these guys here. Anything that touches those alphas is a beta carbon. So this is beta, and this is beta. The least sub beta is where we have our elimination. So between 1, 2, and 3, this is our least sub. So we will have this elimination here. Okay. So keep in mind, our nitrogen will be methylated, and then we'll form this alkene here. Again, this is that example. I realized I actually went over this example earlier. This is that example where if you kind of get caught up in the details of what makes a less sub alkene, this one could also compete, but it won't compete in your brain if you know to look for betas. Cool. All right. Moving on, we have NaNO2 HCl. So we know we're forming the nitrosyl cation. Any nucleophile in solution can capture this. When I look at these two nucleophiles on this proline, this is proline, by the way, we have a carboxylic acid O versus an NH. Nitrogen is going to win this duel for sure. So I'm going to get out this here. Remember, secondary amines make very stable N-nitrosamines. You can imagine here actually that there is a very, very likely interaction, hydrogen bond interaction that can also stabilize here. Whatever the case, right? This proline is going to make a very nice N-nitrosamine. Okay, cool. All right, moving on. We have NaH and we have an alkyl or allyl bromide. So already off the bat, we know that we're forming this here. Looks like if this is 1, 2, and 3, then we'll have 1, 2, and 3 just like this. So 2 position has an ethyl, 3 has 2 methyls, and heat tells me that I'm just going to drop that chain down. I'm just going to draw it on this side here like this. Just remember, if this is 1, 2, 3, this is 3, 2, and 1. So 3 will have the dimethyl, 2 will have the ethyl, and that is our product. Okay. Cool. Now here's a cool little example that's on the third midterm that I'm totally willing to spoil. Let's say that I completely block the ortho positions. What do you guys think is going to happen here? What do you guys think is going to happen? Well, I think that I will get my, well, actually, I'll draw it a little bit forward in time. So let's actually have this here. So what do we think will happen here? Well, I think that, why did it do that? Sorry. I think that we'll still get our Claisen if we do this. But when we think about tautomerization, so when I go ahead and draw the product that I'll get, right? Tautomerization wise, I mean, nothing's really going to happen here. So, you know, you might think, and even it's okay to initially think that we might get stuck here, or maybe we get a reversal in this NR. Okay. Now, very quite often when I ask students this question, people can automatically instinctively see where you need to go here, which is kind of funny. I think people just kind of associate ortho with the para position, but this will actually go para, and I'll give you a second to look at it to see why. But hopefully you can see here, 1, 2, 3, 4, 5, 6. This is just going to do a cope rearrangement. So we have 2, 3, 3s back to back to go to that position here. And again, if I kind of think about how my numbers would work here, this would now just be 1, 2, and 3. There was any substitutions on there. So cool example of tandem cope reactions. The third midterm, by the way, is littered with tandems. I love tandems. They're my favorite reaction. The person that I'm going to work for in the fall, they have also worked on a lot of tandem reactions. I'm looking forward to that. Absolutely beautiful, these cascades. So when you look at the problems and you think you found the answer, if it's not tandeming, you probably did something wrong. Okay, I think like 90% of the questions I wrote were tandems. Cool. All right, so we'll call it there on that. Moving on, we have here an amine, a ketone, and an aldehyde, and a mild acid. This could be a lot of things, right? It could be a manic. It could be reductive amination. I guess those are really the only two things it could be. Remember, reductive amination would need a reductive component like an NABH3CN. Don't see that. We see a ketone, it's an aldehyde, ketone, and an amine. So we know this has to be a manic. So we're going to add in like that. 1, 2, 3, 4, 5. So we'll form the 5-membered ring here, just like that. And then this is where it gets a little tricky. I actually don't know why I wrote this problem. This one is a bit tricky, but this will analyze on this side. Remember, the ketone analyzes, or the less reactive carbonyl analyzes. It'll attack here. 1, 2, 3, 4. Oh, did I draw this wrong? I might have copied this over wrong. This was actually supposed to... Oh, did I miss a carbon? Yikes. I think I might have missed a carbon here. I apologize. So for those of you that tried this and were like, oh, damn, this is kind of impossible. My apologies. I think I copied the chain down wrong here. But well, actually, let's just see if this works. So 1, 2, 3, 4. I feel like this should have worked, but I'll still draw it. What am I? No, I'm definitely messed something up. What did I mess up? Oh, haha. I'm an idiot. It's not on the N. Sorry. You guys are probably pulling your hair apart. Listen to me say this. Some of you guys are gonna go bald listening to how many times I screw this up. 1, 2, 3, 4, 5. So that does make a 5-membered ring. This is why it's important to label your carbons. Even I can make mistakes. And this can be 2. This can be 3, 4, 5. But this is where the ketone is. Ketone is here, which will still again analyze on this position. But this is where it's a little hard to see. So I apologize. This one might have been a little difficult, but you're going to cyclize there. Probably the best way to see this is to form the end, like make the end a bridge. So that you can see what's going on here. We're essentially forming a bridge here. This bridge amine. Yeah. Cool. All right. But again, if this were, let's say this were like NABH3CN here, right? The reaction would essentially have gone to this point here. And then it's like a chemoselectivity question, right? Who do you cyclize? The aldehyde or the ketone? Most likely the aldehyde. Okay. So in this case, I mean, 1, 2, 3, I guess you could technically form some kind of epoxide type thing here, but incredibly, this is 0D would be so strained. Just to form it, right? Just the intermediate to form it would be so goddamn strained. Like this is just a nightmare. Yeah, it's probably not very likely. Okay, cool. All right, call it on that. G, KMNO4, right? That's benzylic H's, so that shouldn't surprise anyone that we'll get the benzylic oxidation here, right? SOCl2 will turn this into Cl, and then amine excess turns this into a primary mid. Extra reaction here that you could have done, like a Hoffman, right? Turns that into NH2 like that. Stuff like that. Maybe lithium aluminum hydride, so you keep the chain. But you reduce that carbonyl. Okay, cool. All right. Our first birch reduction, probably the only one too, because birches aren't that fun. They're all pretty much the same kind of thing, 10 million times over. Oxygen lone pair next to the ring, that's EDG. Carbonyl next to the ring, that's EWG. So when I draw my dearomatization, probably easiest to satisfy the oxygen first by giving it a pi bond, drawing one opposite, and I got that to work, right? Remember, that's different from this and this, right? This would be terrible, but this is totally fine, right? So that's our reduction product there. Let's say that it were 2 EDGs, right? Then we'd want this if this were like not there, right? If they're like an alkyl chain, then this would be perfect. But in this case, right, we want this product here. Cool. All right. NABH3CN should yell at you what exactly we want there. Super, super simple. We're just forming this NC bond. That's it. It's reductive amination, folks. Super simple. And you get, it shouldn't surprise any of you why this reaction is so popular in industry. It's so beautiful. Okay. When it's done, sort of, one thing I will say, I did have some oversight on this. I should have indicated like one equivalent of something. I should have said one equivalent of this, because this actually can continue to react. So technically, I'll actually accept it if you guys had written the tertiary amine. That's totally fine. I can see how that might have been confusing. Cool. Now, J was a reaction that I wrote, and then it turns out you guys didn't need to know it, which is why I didn't talk about it in the review. So womp womp. But basically, urea in these conditions here, first step, turned into diazomethane. And then diazomethane with a carboxylic acid forms an ester, methyl ester. So that's what that would have done. I'll probably replace it with some other question I was thinking of and throw it on here. Cool. All right. Let's break the products. Hopefully that was pretty thorough and makes sense. Mechanisms, pretty straightforward. We kind of went over both of these in the video, but it doesn't hurt to go over this. Remember to always form your NO2 minus. If you start from the your HNO2 is what I'm going to say. Always remember to form that. You can probably start from the HNO2. I'm not sure. It really depends. Sometimes you'll see this written as HONO. HONO it tells you it's starting from the HONO, right? It's HONO. But remember, a lot of this chemistry is making water and kind of kicking it off. So this is our first time making water. We're going to go ahead and kick it off, right? You can use this lone pair to assist. And we get the nitrosyl cation. I'm going to be very lazy here and just kind of draw this here. NO can attack that, or can be attacked by the NH2. And then again, we're going to start off our sequence here. Deprotonations and protonations. So we'll have a deprotonation. And guess what? That proton gets transferred over to the carbonyl. Okay. And then we get a deprotonation. And I apologize. I know I'm being like super lazy with my arrows, but just how I am. And then another protonation, and then you just release water. Okay, cool. All right, so super simple, not too bad. It's in the video too. This one, I don't think you'll be tested on the mechanism for this, and I honestly should have checked. I don't know if it said that you need to know them, but for at least for the EWGs and EUGs. But again, the whole idea is, you kind of throw it in there. I think the easiest set of arrows to use are these here. I guess also if you're uncomfortable with that, like a better set of arrows you can use is this here. Right. I guess that, para position is also, that's known. Right. That is known to be electrophilic on a EWG ring. But again, you always want to form that para anion first. And then get that squared away. Right. I honestly don't even want to redraw the rest of this, but you guys get the point. Right. Damn, my hands are cramping right now. Apologize. My hands are really cramping right now. Just continuous writing for almost 2 hours now. Okay, cool. And then again, electron, and then these will just whatever, right? Cool. I wouldn't stress about this mechanism too much. I don't remember seeing in your annotated slides the full mechanism for this anyways. So I should have written a better question. Cool. Mechanism questions are super easy because you guys have all the mechanisms you need to know. So I would just, if you're really worried, go through the list. There's like a lot of them that's a yes. Just practice them. Right. Cool. All right. Moving on now to the syntheses. Aspirin. This is aspirin, by the way, and this is something. But in synthesis, again, very likely you'll get at least one substitution type reaction, just because they are synthetically the most useful. They're used every single day in industry. Absolutely the best reaction in the world. So how can we solve this one? Just keep in mind, we'll have in mind that we can do snars. Benzyne we'll try not to use, but we can use diazonium, and PD can for sure work too. So we'll have these three squared away. Again, when I kind of look at the end product, I don't really see symptoms for SNAR and N2, sorry. So like, for example, I don't really see the EWGs that I would need for SNAR. So I'm a little wary about that because it looks like we're functionalizing these two carbons. So we're adding to that there. But anyways, for whatever we can do here, we can start with the end product and try to simplify it. So one thing you can always simplify again is derivative bonds. So this ester you can simplify instantly, right? Esters you can make just from acyl halides or anhydrides. So I'll just choose the anhydride this time. But I can simplify that into the salicylic acid. And just from me saying salicylic acid, you guys should see exactly what reaction is here. This is the Colby, right? So this is that very orthoselective reaction where I get CO2 on that ortho position. And so now the question just becomes, how do I get OH onto the ring? And we can really do any of these, right? I mean, I could nitrate, I could reduce, and then I could N2, and then I could OH. So I could do that. That's like three steps to do, right? That's totally possible. I could SNAR, I could do BR, and then I could do NO2. I could do the substitution. Okay. I could then reduce NO2 into NH2 and then into N2. And then think about it. How do I turn N2 plus into just H? Because I have to make it disappear, right? I can turn it into, I could use H3PO4, or sorry, H3PO2 to turn it into H. So I could totally do that, but that's really, really long. But hey, guess what? I could also just do this. I could brominate this. And then I could literally just use PD, PPH3, and then whatever, NaOH would probably work here, right? Probably even bicarbonate will work because bicarbonate is usually done in like a basic solution of water. Okay. So all three actually had a possibility. I mean, technically you could also even said benzyne if you wanted to. This is the only time benzyne is acceptable, right? Because it's like no regiochemical disaster or mess here. But look at the wide variety of things you could do, right? I mean, you could have done the N2, that would have worked, just really long, right? Because you'd have to, sorry, the SNAR, you could have done the SNAR, it's just very long, because you'd have to NO2 here and then get rid of the NO2 via H3PO2 of a diazonium. So that's very long, but it's possible. You could have gone through the N2, which is just nitrating, reducing, N2ing, so we can actually even write this out. So what you could have done is just done a NO2 here, and then turn this into NH2, go to N2 plus, and then turn this into OH, right? That could have worked too. And technically the N2 to OH can be one step. You just got to heat up you just have to have it higher than 0C, and then hydrolysis will occur as you make the N2. So that works too, right? All these are possible. So really the point of this one was to kind of show you that, a lot of possibilities on how to get to the OH. But usually the shortest is the cheat code, right? If there's absolutely no requirement of an NO2, use the cheat code. It's so much easier. Okay. Cool. All right. So that's the first synthesis. Again, I guess a good way to know that I wanted to do SNAR might have been if I left NO2 there, or maybe I turned this into CN, right? CN would have been an interesting one because then I could trace back to the phenol with the CN here. And it's like, oh, okay. So in order to get that phenol there, I have a para group, and that para group could have come from like an NO2, right? That's just NH2 into N2 into CN. And then, I mean, obviously, again, the NO2 this could come from a BR. So this would have been a really long one, but it's totally possible, right? Again, that was that common sequence that I mentioned in the review. That's a very common sequence, right? So the common sequence is going from, because I know some of you might not watch the review, it's going from BR to NO2BR to some nucleophile here to, and then doing the NH2, N2, and then some nucleophile here. Okay. Common sequence. Cool. All right. Call it there on that. This one is a bit of a doozy, but it shouldn't be too bad. Hopefully you guys recognize the shape here. We have a diphenol, which we can kind of trace back to a quinone, right? And so if I trace that back to a quinone, hopefully you guys can see what happened here. Sorry. This is a Diels-Alder type reaction. We have the cyclohexene, the quinone on here. So I can cut these bonds here, right? Get that diene off. As you can see, the quinone is what we added in, right, to this Diels-Alder. Okay. So the question becomes, how do I turn my amine into two alkenes? Super simple, right? It's just two Hoffmans. So this is, again, that example I was talking about where you have to be very careful with your cycles. A lot of people, when this kind of question is asked, instinctively just go ahead and do both cycles in one step, but it's two cycles. So you have to do them separately. Okay. So there you go. Cool. Very, very cool, these type of reactions. I mean, ring alkenes kind of open up what you can do with them. I suppose another crazy thing you could possibly do, let's see. I suppose you could maybe open this up into 1, 2, 3, 4, 5. Oh no, actually no, this would never work actually. It would have to be a 7, I guess it would have to be a 7-membered ring if I wanted this to work. Right, I guess if you wanted to, like if you did a diene here, this diene would be the 1, 1, 2, 3, 4, 5, 1, 5, or the one, like it's a cope basically. So this would cope, but I mean this is super choreographed. It has to be specifically this in order for it to work. Okay, but yeah, anytime you see an alkene and an amine, especially on together, right, that should indicate to you that there was some kind of Hoffman type reaction. And just in general, right, if you see an amine transforming into an alkene, or you need an alkene, I want you guys to think Hoffman, probably the easiest way. Cool. All right, those syntheses should have been pretty straightforward. These ones are a lot harder, actually. Actually, just looking at them, you can see that they're a lot harder. So definitely, work on your retrosynthesis. It'll make things a lot easier. Cool. All right, explanation. So I didn't get a lot of time to talk about explanations or possible explanations, but we'll take some time right now. I mean, we'll probably round out the hour just to get it to whatever it is. I mean, I know we're about to hit 3, so we'll just probably round out the hour on that. Actually, let's just do general knowledge really quickly. So Gabriel reagent is phthalimide. So Gabriel reagent, it releases a primary amine. I just use, buzzwords, honestly. This is just taking words on your study sheet and just making sentences out of them. Claisen rearrangement involves allyl vinyl ether, right? Which upon heating forms gamma delta unsaturated carbonyl. Okay, cool. So get that out of the way. And then, oh, damn, these are actually, so we'll do this one first. So circle the molecule that's most reactive SNAR. So remember, SNAR is ortho-para EWG by resonance. So that's not that's not EWG by resonance. These are EDGs. So that leaves these two. This is ortho-para. This is ortho-ortho. Ortho-ortho, just more reactive because of inductive effect. Okay, that's pretty simple. Cool. We have a tier most basic molecule. So this, if you want to, you can go back and review the very quick acid-base stuff that we talked about. Remember that we can kind of oh, okay. So I realize now that there was one group I should have talked about before doing this, because I know what you guys are going to lean towards. So a lot of you are probably instantly going to circle this, and I can see why. I would totally understand why you guys did that, because you see here sp2, sp2, and then sp2, right? Because this nitrogen lone pair, this nitrogen lone pair, and then this can resonate, right? So this is a nitrogen lone pair in an sp2 carbon or oxygen, sorry. So it's easy to just instantly go here. I forgot to mention the one exception is this group here. So if I wanted to go through very quickly the pKa's, this is similar to the imidazole system that I gave a 7. This is an amide, which actually resonates into the oxygen. And oxygen's not basic at all, right? It's very, well, at least in this context, it's not. It's about -1. This here is a guanidino group. And guanidinos are incredibly basic. They're actually all the way up at 12, which is a little north of what you would give an sp3 amine. So very bad question on my part. I apologize. I should have written this better, right? But these two nitrogen lone pairs, right, they give a lot of density to the nitrogen. A lot of polarization towards the nitrogen. So it's incredibly basic. So this question was a bit unfair. I'll make a note of that. I kind of egoed on that one. But if you guys chose this, then I'm totally okay with that, because it means you understood what I had said at the time. So my bad. Cool. All right. But with that being said, let's just get into explanations and how to do this one. So Hoffman elimination, remember, usually is CH3I. So let's understand why this works better than the other groups. So when I do the Hoffman elimination here, right, obviously exhaustive methylation works very fine. And then we'll get the elimination on the beta carbon here, which again, usually what we do is we label alpha carbons. And then if there's a beta, we label the beta, right? These guys don't have betas. Wink, wink, right? But when I use the ethyls in this reaction, again, I'll get the exhaustive ethylation. But now when I consider my alphas, right, these guys, and these guys, and these guys, I just introduced 3 new beta carbons that are way better than the beta carbon that I had back here. Okay, I have CH3s that are less sub than the CH2. So in fact, instead, what I'm actually going to get are the eliminations on I'm going to get these eliminations here on the amine, as opposed to getting, this should be not there. I'm going to get this elimination on the amine as opposed to getting the other one that we really wanted. So this is why we do exhaustive methylation and not exhaustive ethylation or propylation or butylation, because we will accidentally, we want to reduce the chance of eliminating. So that's why we use these methyls, right? They can't eliminate. They're always going to stick there. Okay, so absolutely no competition. So that's a type of explanation question you can get, right? Other types of explanation questions, right? Again, all hinge on understanding concepts in this class. For example, why it is that if I have a CF3 para to a BR, that's not as, or a CL, that's not as great for SNAR as having an NO2, right? Great explanation there is that, hey, that's an EWG that's by resonance. And that's what we need, right? We need a vacuum. We need a resonance electron vacuum. This is a sigma donator, right? This is a sigma withdrawer is what I meant to say. So EWG by induction. So not the greatest, right? Not the greatest to get there, right? Same thing with if you ask, why does NO2 being meta is not as good as being para? Why is this worse than being here, right? Because being para again promotes the SNAR, right? Being meta promotes the benzyne, and benzyne is super rigorous, right? Pretty terrible. Why might this substitution via the N2 not work so well? Right? Because again, if I form this N2, that's the best leaving group in the world. That's going to instantly ionize into the cation, and then the H is going to, move right over. It's going to just jump right over instantly, right? Things like that. Those are the things that are, the main tests of knowledge. I don't really think there's going to be anything from last midterm that will show up. Like, for example, why are phenol esters more reactive than normal esters? We talked about this for last midterm. Reason for this being is that phenol esters are better leaving groups than normal esters because of the pKa difference, 8 to 10 versus 15 to 17. So better the leaving group, right? The more reactive. So that maybe might come up. I'm not sure, but probably not very likely. But yeah, when you think of explanations, when you're going through your study guide, you want to look for reactions where there's some kind of exception or there's some kind of rule you have to follow by. Like another one I can think of instantly is the Colby-Schmidt, right? Because Colby-Schmidt, we talked about, that's the Na that is, it's holding the CO2 and the OH, right? It forces that ortho attack, right? That's a good thing to talk about. Or, right, phenolic resins, right? Why is it that when we make resins that everything has to be ortho-para? It's because for one reason for this is because we form ortho and para quinomythides. So we're always going through like one of these guys here. I know I'm drawing it on one, but you have to get my point. The other is that as a nucleophile, right, phenols can only add on the ortho and para positions or attack by those ortho para positions. Okay, so everything is kind of added, it's really what you're looking for are the exceptions, right? The rules. I know we didn't really talk about this, but it could be a good concept question in the class, right? Why does CF3, right? Why is that promote the only, or why is it the only one that promotes a very selective benzene type reaction? Right. So why is it that when we have CF3, our nucleophile tends to add meta as opposed to ortho? It's because when it does, right, we get that anion next to that withdrawing group that polarizes, or even just we can think from the benzene intermediate, right? There is a polarization of that pi bond towards the CF3. So the most electrophilic carbon is the one farthest away. You also think of it as the resulting anion is stabilized via induction, so higher product distribution. Okay, cool. So, I mean, there's a couple more problems I've written. There wasn't really like an explain question because I can only think of two. One was really hard, and I put on midterm 3, and the other one is the one you see now. But now you see all the other ones that are possible, right? Go through your questions and your terms and concepts in your study guide, and look at things that might have exceptions to them, right? I mean, there's a lot of things, right? I mean, that one thing that I mentioned, right, which is normally copes, right, are in equilibrium, right? But why is it that when you add an alcohol on this 3 position, right, it suddenly gets super fast? It's because a big driving force here is that once you get that tautomerization, once you get that sigmatropic reaction, you get a tautomerization into the ketone, the stronger bond, or aldehyde, I guess, in this case. Okay, so that's like another one to think about, right? Yeah, cool. All right, so we'll call it there just because I'm getting tired. I think it's almost been 3 hours anyways. So we'll call it here. Any questions, any mistakes, let me know. I'm definitely going to do, I will definitely write the keys for 2 and 3 and just send them out. If I get time, I'll definitely do 2. I probably won't do 3 though. So if there's any questions on 3, you'll have to ask me or ask someone in the chat. Okay, cool. I mean, looking at 2, just to give some general tips, I mean, that just kind of amped up the difficulty to make you think a little bit. Some of these that are my favorite, I mean, really my only favorite is probably D. D is probably my most favorite on this. So make sure you think about D the most to make sure you're doing it correctly. That was my favorite. Mechanisms should be fine, pretty fair game. The syntheses look pretty terrible. All I'll tell you is that this NO I had to add in as a formality, because if I didn't, I know someone was going to say, doesn't the NO add in the last step? So that's my hint to you. I only added in the NO because I knew someone would ask me, why doesn't the NO add in the last step? So that kind of tells you that the last step is probably an NaNO2 step. And then you can kind of work backwards and think about what it is that you're adding, right, to the molecule. What shapes, or maybe not shapes, so what it is that you might want to do. And I'll tell you what, this nitrogen placement was a tricky one. Okay, I know what you guys might want to think to do here. You have to be very, very clever. Okay, same thing with this one. If you, if you read the chat, you'll see how I did it, because I walked someone through this. But again, retro is your pal here. Retro will save you on this question. Go backwards. When I look at this, I see a phenol. I see an amino phenol with an alkyl chain ortho to the phenol. Is there a reaction there that I can think of that I can, at least for the time, reduce the complexity of, so I can get to a less complex product, right? Then I just think about, how can I get the OH there, right? How can I get the N there? Where in the world did this N come from, right? Where are the starting materials, stuff like that. Okay, cool. But yeah, with that, we'll call it there. You guys have a good one.